since 1986. During his 30 years in the laboratory, Dr. Gieselman educated a new generation of leaders in the field of pulse power, which are in decision-making positions in National and Department of Defense DoD laboratories. Since the early 1990s, Dr. Gieselman worked on solid-state power electronics for pulse power applications. He worked on high-power density designs for continuous operation in the 500 kilowatt level for 60 kV DC, as well as 13.8 kV AC outputs for ship-borne and airborne applications. Dr. Gieselman has extensive experience with wind power and renewable energy systems in both technology and research capacity. He was the lead in procuring a 1 megawatt hour battery storage system in complement to a wind farm at Reese Technology Center in Lubbock, Texas, and install a synchronous phasor network to monitor the SPP grid in the Texas Panhandle. He is currently a co-PI on the $13 million GLEAM project in Reese Technology Center. He was the committee chair of 34 graduate students and served on the committees of 66 others. To date, Dr. Gieselman has published more than 160 articles in the form of journal papers, conference proceedings, and book chapters. He has participated in funding research totaling over $33 million. So with that introduction, Mike, the podium is yours. Thank you.
Thank you. Keep the presentation, as we mentioned.
Oh, okay. So the deal was that we present your presentation. We don't present. Okay, I'm sorry. Wrong word. We don't present, but we forward the slides at your direction.
Yes.
So you should be able to see the slides that you prepared, and please tell us when to forward it. And Dan Kelly would forward them.
Okay, very good. Thank you for the workshop. Thank me is very honored. Very honored to the NSF and more. I'm very impressed about the new Lives lab. I mean, this is a leap forward. It really is, and you know the integration and the ED space, and you can get rid on this. This is great. Great workshop. I show a bit about maybe next shows the campus and.
Hey, Mike, I'm getting a message that sound quality is a little poor. Is that something at your end, or it's?
I don't know. Having the very first internet, I'm traveling. I settle my flight back to the States tomorrow morning. So is the sun approximately?
No, what I could do is I could stop my video if that would improve, and maybe you could stop your video.
Oh,
I mean, you could not.
Stop my.
Okay, I'll stop sharing my video too.
That's for bandwidth. Okay. Is that bad?
Yeah, a little better.
Okay. I did Zoom meetings from here. Good. It's video. So get to the next.
The quality is still a little bit bad. Did you say next slide? Sorry.
Yeah.
Okay.
To the campus, next slide was just where it is. Load. Go next.
Yeah, I'm sorry. We're still not getting much of what you're saying.
you try slide. Yeah, Zoom meeting here, and it worked out great. Use same equipment.
Do you perhaps have like a Ethernet cable that you could plug in if you're on wireless? I don't know if that'll help or not.
No, it's an iPad, but I've done this before from that equipment, and I
Okay.
stopped it.
Well, you're coming through
else.
clear now, so maybe we can
Okay.
try moving forward. Yeah.
Okay, good. Yeah, go to the next slide. I mean, this shows where Lubbock is located. It's in the Texas Panhandle, and we have plenty of space and wind and solar. And then if you want to go to the next slide. And so Texas is, most of Texas is ERCOT, and in ERCOT, wind is absolutely dominating in the United States, and that was a deliberate decision that the governor of Texas at the time with Perry made, and the utilities, and they built so-called CREZ lines, and those CREZ lines, they're for competitive renewable energy to basically get power from competitive renewable energy centers and places to get back to Central Texas. And Lubbock is going to join ERCOT in a few years, and then we have on the next slide we can show that we have on this Reese Technology Center, we have a large renewable energy microgrid now in place that we are currently operating, and that is a big battery that's part of it. And then we also have solar and a diesel. That's then on the next slide. And so it shows a view of the solar array, and then it shows the microgrid and the diesel in front of it, and the control center. And so we can run a microgrid, and it's just it's good that we have capabilities to just also do some research in the fields that we teach, to make credible offerings, and to also allow students to do graduate work. And so on the next slide are the courses. And so we took the CUSP courses and actually put them into the curriculum of the College of Engineering at Texas Tech University. And so they have a engineering level designation. They are called ENGR, and then a number. The first number is a 5 that indicates master's level graduate. The next number is a 3, that's 3 credit hours, and the last 2 numbers are the running number. And so those are all the CUSP courses that we've had. And if you go to also the next slide and the next one. So it shows, I mean, this is of course for multiple audiences. That shows all the courses and what they are, and who developed them, and the credible credentials of the people that developed them. And so let's go forward. And go one more. And so we created the courses in the catalog and got approvals at all levels. And then we advertised the courses, and we need to do some more of that. And we started teaching these courses now. And so if you go further, and then those are the courses. They have these ENGR numbers, and like I said, 53 and then a running number. And then you basically have to put them into a system that's called Curriculog. And so you have to run the new proposals of a course or a whole sequence of courses through all kinds of levels at the university, and then get it approved at the Texas Higher Education Coordinating Board. And there's, then if you go forward, this is what that basically looks like. And so you put these courses into the system, and then they go from committee to committee to committee at the university level and get approved. And you need to supply a syllabus, you need to supply a reason why you wanting to include those courses. They go start at the, if it's an ENGR course, they start at the dean's office, dean of engineering, and then they go forward to the provost's office, they go to the graduate school, and then they go further on along and finally get approved. And so if you go forward, those are then these other courses. And so we got this done, and we have at the college level engineering courseware, and we taught this power electronic, the power generation operation and control course in the fall of 2019, and the instructor was Dr. Wallenberg. And so this is the interface for the students, and it's really, really well managed by the college. And so we had about 10 students in the course. And this is then the log on screen. The students that enroll, they get to log on to this. And there's then videos available and homework and additional materials and so on. And then tests can be administered and grades are then given. So if you go forward, so here's then when you click on the links, then you see, for example, the assignments, you see additional materials, you see also the videos, the link to the videos. And so then on the next slide, see that he was the professor teaching it, Dr. Wallenberg. And so then if you go forward, this is then the actual, that was the actual sequence of lectures that were available to the students. And we show some of these. So if you go forward to the next slide and then one more. So here, this is an excerpt from the materials that the students saw on the website. So this is a website you can just go on and log on from anywhere. And I've been using it for probably almost 15 years, probably. I teach just about everything exclusively on this system, and it's extremely well managed by the College of Engineering. And so just about every course that I've taught for the last 15 years has a face-to-face section and a distance section. And so that was also nice because when we went to all distance in the spring here, this spring, it was a fairly seamless transition. And so let's go see the next slide. Yeah. So this shows the videos, and so we have studios where we can take videos, and so you can have two. We typically in the studios where I usually teach, we record two streams. First is the instructor, and the other one is then the screen capture, and you can switch between the two. Or we take the CUSP courses, we take the videos and put them on there, and we have quite a few courses already available now with all the materials in this platform, so students can take those. And so let's go on the next slide. So this is something that I taught that this spring, and on this system. And then on the next slide. So this is just basically the curriculum for it. This is the intro course of the sequence for power systems. And so then we have a number of other classes available. Let's go forward. And we advertised it in T&D World. And we need to further advertise it on the US Power. We did, but we need to do that. That T&D World was rather expensive. I think that costs about $5,000 or something to advertise. But we have a contact now, and to do that, and the US Power listserv faculty, we can advertise it there. And then, of course, Navy and DoD can certainly do that. So we have available the electric power systems, we have electricity markets, we have power system protection, and we added more courses that are ready to go on the system in the College of Engineering. We also have, of course, the power systems operations and control from Dr. Wallenberg, that course. So if we go to the next slide. So here that shows two new courses we added, Advanced Power Electronics 1, and then Vector Control of Drives is available on the system for students to take. I think, let's see this. Go to the next. All right. So then a couple of the students that took that course from Dr. Wallenberg last fall actually continued to do research based on that. So they expanded a term paper, and it's submitted for a journal. So that's a good outcome. And the topic is, can a 100% renewable power system be successfully built? And so that is currently a interaction with two of the students from the 5323 course from last fall. That's developed into a nice journal paper. So, and so that's a summary of that research, and that is currently being reviewed. So that is, thank you for your time. That's my presentation. And if you have any questions, please let me know. What was the audio better?
Yes, it was just fine. Thanks.
Okay. Oh, great. Because I've done and I shut down everything here that could hog any bandwidth. So I've done quite a few. You know, as a department chair, you always have to do something. There's always something going on, and so I had quite a few Zoom meetings going on, and it worked fine.
Well, great. Yeah, it came through just fine after that beginning, so no
Great.
worries.
So I'll unmute myself, and I'll also show my video here. Somewhere here, start video. Okay, I'm a little new to Zoom here, so pardon me for being a little clumsy. So thank you so much, Mike. You know, in times of COVID and even before, you know, we were kind of prophetic that
Yeah.
we kind of knew that we should go towards online education, and especially given the cost. And also, if you want to reach practicing engineers, there
Yes.
are thousands of them out there, right? So
Yes.
this is really, as I see it, moving forward, this is an extremely important task that we have for us, you know, to somehow package these courses such that, and not necessarily for a master's degree, but that'll be great, but just one course at a time, somebody wants to take it, or, you know, we can package it as certificates. So I just finished writing a proposal to NSF. That's what we faculty do, right? Write proposals all the time. Okay, that's where we spend our time. So it turns out that universities that are offering online courses, these online courses are more expensive than on-campus courses. We are talking before COVID. So take an example in our College of Science and Engineering. If you take a graduate course, you have to pay $100 per credit. That means for 3 credits, you have to pay $300 more for a technology fee. Okay, so only way these courses would become cheap online if these brick and mortar universities disappear. Okay, we don't want that, but that may
No,
be
we don't quite want that.
but that may be that's the only way to make it cheaper, because if you have brick and mortar and you have all the infrastructure, this online courses, you know, as they stand there. But you know, some university may, you know, your university may decide a separate branch that offers online courses, right? And they could be cheaper. So I think we really need to put our heads together to see how we can continue this on this path with all we have done, all the experts that we have who have developed this, and make it as low cost as we can. So Mike,
I think, I think we should make it as a supplement to the normal program for practicing engineers that are out there.
Sure. And make it clear that this is an online degree, right? So somebody who wants to, you know, credentialize it, they know where it came from and what procedure it was offered, and it can turn out to be better than on-campus education, because here you're taking a course, for example, from Professor Wallenberg, okay, who wrote the book, right?
Who wrote the book.
Right. And if I were teaching it, I'll be just regurgitating what he has written, right? So it's it's quite a bit different. So in that case, anyway, enough said. So thank you so much for your effort. And if there are any questions through the chat box, Mike, we'll share it with you. And with your permission, with your slides and presentation, we'll upload to our CUSP.
Yes, of course. Okay. Yes.
So
please upload them.
Stay safe, and I understand you're coming to us from Germany, right?
Yes, and I'm flying back tomorrow morning.
Okay. So have a good, safe flight, and you know, and you know, all the best to you. You know.
Thanks.
Maintain the social distancing even on the plane.
No, and the planes are empty these days.
Okay.
It's easy.
Okay. You fly American, right?
Yes.
Yeah. Okay. All right.
Planes are empty.
Yeah. Okay. Yeah,
no, they are.
Okay. Yeah. All right, Mike. Thank you so much. Thank you.
Thank you.
See you in person soon, sometime. Yeah. Bye-bye.
Bye-bye.
All right, my friends. It's a few minutes to 2 o'clock. So yours truly has to go into the power electronics track and electric drives track that we are on, which is also the general session. Dr. Siddharth Raju will take over, and I probably should log off from this track because I don't know if you can log into two separate tracks simultaneously. And Professor Robbins is the host of Power Electronics track. So I'll wait till he allows me to join as a participant. So I'm logging off at this stage. So see you at 4 o'clock. From me. But otherwise, all these 1 hour long 3-track session continue. So there is Siddharth. So Siddharth, I'm logging off, okay, on this track. Okay. So I'm logging off, Siddharth. Can you hear me?
Hi, Professor, I can hear you.
Yeah. So I'm going to log off, okay?
Sure, Professor.
Yeah. Thank you.
Hello all. I hope you can hear me. Today in this session, we'll be looking at one of the courses that's taught in the University of Minnesota. It is the Advanced Electric Drives Lab, a graduate level course. And the way the Professor Mohan teaches it is students do not need to have any prerequisite except like a little bit of knowledge of control system. And other than that, they have no requirement of having done power electronics or electric drives to be able to attend this class and be able to do advanced motor control topics. So it starts off with very basic elements of power electronics, magnetic circuits, and then builds on to a little bit of control system, and then about DC motor and AC motor drives in steady state. And then finally, it goes into advanced vector control topics, and including sensor vector control, sensorless vector control, DFIG control, and etc. So in this session, it's a brief 1 hour session. I'll try to cover as much of the topics that as possible. And we'll also see a couple of simulations and hardware experiments to kind of keep it a little bit interesting. I won't be able to go into too much of a detail. I'll just give like an overview, and anybody who has some basic understanding should be able to kind of dig in deeper and figure out the math and the equations later. But I just hope to cover like the whole bunch of ideas that we go over the semester long course, and hopefully condense it into 1 hour. Okay, so here's the outline for today's lecture. We'll be looking at the introduction and the reason why we are learning electric drives and their control. To start off with, we'll look at DC motor drives and how to do speed control for DC motor drives. At the end of the day, with AC motor drives, we are trying to achieve the same performance as a DC motor. You want to have a step response in your speed for a step reference speed. And irrespective of the load applied, you want the speed to remain a constant. So it all starts with the DC motor, and AC motor is basically, you can look at it as two independent DC motor of some sense. And I'll explain more detail as to what I mean as we go into detail. So once we know the control of a DC motor, the rest of it is pretty straightforward. It's just like mathematical mixing it up here and there so that the AC motor looks like a DC motor. So that's what we'll look in the second part of the session about DC motor and the speed control. We'll do some simulation and some hardware results, a hardware experiment. And the third part of the session is looking into AC machines and seeing how they are distributed and getting a brief understanding of AC machine analysis using space vectors, understand what space vectors are and how it's used to model AC machines. And the last but before section is about DQ analysis of an induction motor. And the last part is extending the same to PMAC motor, vector control. Okay, so what we plan to achieve at the end of this session is basically be able to do something like this. So here we have an induction motor model, and we are going to be able to see, understand the concept that goes behind running an induction motor in vector control, where the speed of the motor remains constant even when a load torque is applied to it. So as you can see here, I apply a load torque and the speed still remains a constant at the desired 100 radians per second. So at the end of the session, this is what we want to achieve. So we'll start out with doing this for a DC motor, and then extend it to a induction motor, and then take it from there to a PMSM motor. And if at any point, if anybody has any questions, just raise a question in the chat window, and as soon as I see it, I'll respond to you. And if I'm going too fast, or if you miss out any of the points that I said, just let me know and I can repeat it again. So this course, as I mentioned, is a combination of 3 courses combined together. The power electronics course, the basic drives course, and the advanced drive course. So all of this is combined and taught in a semester-long course with some elements taken from the power electronics and some elements taken from the machines drive, and all of it from the advanced electrics drive. And as I mentioned earlier, there is no prerequisite for this course other than just the basic understanding of control system, just an understanding of Bode plot and the phase margin, gain margin. Those are the concepts that's required. Other than that, nothing else is necessary for this course. So the topics that are covered in this course are broken down into 3 parts. The first one is the fundamental of electric drives, where we cover the reason why we do this, the energy conservation aspect of going to electric drives rather than directly line-driven motors. And then we look at basic concepts of magnetic concepts like flux linkages and all of those aspects. And then we look at power electronics, the basic, again, what a switching power pole is, how it's used to generate a variable voltage, output voltage from a fixed DC voltage, and then how using common mode voltage injection, you can get AC output voltage from DC input voltages using a 3-phase inverter. So those are the concepts that are covered in the first fundamental part, and also the control part of it, how to design a PA controller for a first order transfer function, which is basically a DC motor model. So that part we'll cover along with the switch power electronics. The basic magnetic concept I'm not going to be looking into in this lecture because it goes into unnecessary detail, which most of the people attending this workshop must be familiar with anyways. So the second part of the lecture session is about steady state operation of AC machines. And this would include space vector modulation of an inverter and understanding about AC machines, how these windings are distributed in an PMAC machine and induction motor, and how they respond in steady state. Again, I'll just cover like a brief 1 or 2 topics in this and skip the rest of it for the most part because the topic of interest for us is the last part, which is the vector control of AC machines, where we'll go again into a little bit detail of why we need DQ transformation and how it helps in simplifying the motor model design, and then look at some of the control aspects of induction motor so that the speed can be maintained constant even when the load changes. So this we will tie it back to DC motor speed loop control, which we did in part 1. And then the final would be the PMSM vector control. In addition, there are like a bunch of other topics covered in this as well in the course and as well as the website material available on CUSP. Some of those are the sensorless vector control of induction motor, and then interior permanent magnet motor control, vector control, again sensorless, and DFIG control as well as reluctance motor control, as stepper motor control. So all of those topics are auxiliary topics. We won't cover it in this lecture, but it's just an extension of whatever we're going to look at it in the current session. So all of these 3 textbooks have been combined into a single textbook that's being published by Wiley this coming August. And it just takes the bare minimum necessary from each of these courses to be able to go over all the topics that I mentioned before within a semester. So, okay, so why do we teach this course? The motivation behind this course, most of the energy that's consumed is now currently being consumed by motors that are not, that are directly connected, line connected, and not being driven by a drive. So there's significant amount of energy that can be saved if we can move from direct line connection to having an inverter in between. So US consumed about 96 quadrillion BTUs in 2013, and this shows a pie chart of the which sector consumed how much percentage of the energy. As mentioned, 32% was in the commercial sector, industrial sector, sorry, and 39% was in the residential and the commercial sector combined. So here's a breakdown of where all this energy is being consumed in electric drives. So most of it is, significant portion of it goes into air conditioning system. So even making this system couple of percentage efficient would save significant amount of energy in terms of that's being generated, as well as significant consumption, savings in the consumption side as well. And here's a breakdown on the commercial end. As again, most of the expenditure is on AC air conditioning in the commercial sector as well. So even minor reduction in the power consumption by using more efficient drives could save significant amount of energy. So here are some numbers for how much energy can be saved. And if we were to save, do a motor upgrades, go from line driven to electric drives based, as well as make these electric drives more energy efficient, the total energy that is saved would be about 4% of the energy generated. So that's significant amount of energy saving that can be achieved by just upgrading drives. Okay, so there's more motivation to going to drives other than just energy saving. And one of the primary motivation is to do precise control. So this could be position control, speed control, or torque control. And that each of it has their own application. Like you would have position control applications in, say, robotic assembly plants, where you want the robotic arm to, like a car assembly plant, where you want to move it from one position to another and then fix some screws and stuff. You would have place where you want to do torque control, like in a conveyor belt, where you have some load being added and you want to keep propelling it at some constant level of torque. Or even when you're in an electric car, you would have torque control at lower speeds and stuff. And speed control, the most common, obvious. You can use it in electric drives in cars. It could be used in ventilation systems. So each of it is just another extension. So you extend the position control with another loop, it becomes speed control. And you extend the speed control with another loop, it becomes torque control. Sorry, you extend the position control, you extend the torque control with another loop, it becomes speed control. And the speed control with another loop becomes position control. We'll go over the loop structure and everything at a later stage in this lecture. But for now, we'll just go like an overview of what we are looking into. So most of the application requires efficiency, which in turn requires maximum power per ampere. So if you're, say you have your drive has an efficiency of 90%, that would basically in turn limit the amount of maximum torque that you can produce in your drive. So if you increase your efficiency, you're going to effectively get more torque for the same amount of current. So that's another reason why you want to have electric drives that are more efficient. In addition to the power saving potential, is just to increase the amount of torque that can be achieved by using the same voltage, input voltage, without changing the input voltage or the inverter structure. Just making the drives efficient would just mean that you get more torque out of it using the same system. Also, if you have more torque, it means you can control your system more at a faster rate, available of more amount of. So if you'll for the most part drive your drive at maximum at the rated flux condition, so that you can do precise speed control at very fast pace. So all of this is dependent on having that increased efficiency in your drive. So what are we trying to achieve by using a drive and speed control? So say you have a conveyor belt and you have some weight that drops on the conveyor belt. Irrespective of what drops on the conveyor belt, you want the conveyor belt to be going at a constant speed. So that's what is shown here. Say at time 0, you add a load to your conveyor belt, you want the speed to remain a constant. So this is the idealized scenario where the speed is always a constant irrespective of the load that's applied to it. In a practical system, the speed would dip a little bit, but if your controller design is good enough, the speed should be able to catch up back again and settle down to the desired speed. So that's what we'll try to achieve, and we'll try to narrow down the band in which the speed dips by using faster and faster response. But this comes at a cost. It would just mean that you'd require a more higher transient current. But again, we look at it as we go into details. But the ideal response is you want the speed to remain a constant irrespective of what load torque is added to the system. Okay, so what is electric drives? So you have a mechanical system on the right, which is basically your load that is connected. This could be a conveyor belt or an elevator system or a ventilation fan. It could be any combination. The mechanical system, which is coupled to the electrical system, and this you're driving electrical machine, and this you're driving by a electrical system, which is basically coming from a grid source or a DC power supply. And then you have a power processing unit, which is converting from one voltage and frequency to another voltage and frequency. So if it is an AC to AC converter, it's going to convert from one AC voltage and frequency to another AC voltage and frequency. And if it's a DC to AC converter, it's going to convert from DC voltage to desired AC voltage, magnitude and frequency. So that's what we want to try and do with the electric drives that we have here. And adding on this power electronic unit here allows us to control what voltage comes out at the output. And that in turn allows us to control what the speed of the motor is, or where the position of the motor is, or the torque that's being generated by the motor. So there are two basic converters that we use to achieve this. In a DC converter, we use a full bridge converter. So it has two legs. Using these two legs, you can make the voltage at the output go from positive DC bus, 0, or negative DC bus. So those are the three combination of voltages that you can generate. So if say your switch is A switch is connected to the top DC bus and your B switch is connected to the bottom DC bus, you get plus VDC. And if A is connected to the bottom DC bus and B is connected to the top DC bus, you get negative VDC. And say if A is connected to top and B is connected to top, or A is connected to bottom and B is connected to the bottom, you get 0 at the output voltage. So those are the three output voltages that you can generate. And if you adjust the time period with which you use the positive and the 0 or the negative and the 0, you can do modulation. So say if I apply DC bus voltage for 50% of the time, and the rest 50% of the time I apply 0 voltage, that means my average voltage is going to be VDC by 2. And similarly, I can adjust the percentage amount of time I apply the DC and the 0 to get different voltages between minus VDC and plus VDC. So that's what we would do for DC motor control. And for AC motor control, we just add one more leg to the system. So you have 3 phase, A, B, and C. And the neutral point is maintained at VDC by 2 by some control algorithm that we'll go later. And the output voltage just goes from plus to minus of a sine wave, positive VDC by 2. So if you are using sine PWM, you would get your output phase voltage to go from 2 by 3 times 0.75 into plus VDC to minus VDC, similar to 2 by 3 times 0.75. So that's about 0.5. And if you're going to do SVPWM, you get a little bit increased modulation index of 0.866. Okay, so let's just look at one leg of a converter. So you have DC bus voltage, and you control the amount of time the switch is on and off to control the output voltage. And so this is the output voltage at this point is going to be a switched voltage. It's going to be on and off. So it'll be VDC and 0, VDC and 0. And on at the output, if you connect a system that has, which is equivalent to a low pass filter 1 by SL plus R, that has a time constant that is much lower than the switching frequency, then it's just going to look at the average voltage rather than the switching voltage. So that's what we are trying to achieve by using a power converter. We switched this at a very high frequency that the motor can only see the average response of it, because its time constant is much higher than the switching frequency time constant. Okay, so we controlled VDC by controlling the output voltage, by controlling the control voltage here. So the control block that I showed here, PWM-IC, what it basically does is it generates a triangle waveform, and it has a control voltage here. And if the control voltage is greater than the triangle, you have an output which is turned on. And if the control voltage is lesser than the triangle waveform, the output voltage is turned off. And if you look at the average of this on and off waveform, would be your desired output voltage. So you adjust the control voltage to the desired value so that your output voltage average represents whatever is required. And the algorithm to do this would be to have a common mode voltage VDC by 2. Again, I won't go into the details of it, the lecture available on the CUSP website would be able to dives into more detail. So we want to target more towards vector control. So I'll skip over most of the inner workings and details of it. So basically the output voltage would be equal to whatever the DC bus voltage is divided by 2 plus your DC bus voltage by 2 divided by your triangle peak and into your control voltage. So adjusting your VCA, the control voltage, you can adjust whatever your output voltage is going to be from plus or minus VDC. Okay, from 0 to plus VDC, because we just are using one single leg in this example. So you can have either maximum VDC or you can have 0 in case this is connected to the bottom leg. So with only unipolar voltage, you can control only one direction of a motor. So if you have a DC motor and if your voltage goes from 0 to say 40 volts, your speed is say going to go from 0 to 200 radians per second. And to be able to get negative speed as well, or if you while you're using positive speed, you want to get braking, in which case you need to apply negative voltage or voltage lower than the back EMF, in which case you would need bipolar legs. So that's what we achieve here. So you use 2 legs of an inverter rather than a single leg to get bipolar output voltage. So as I mentioned earlier, if you connect the top leg, top switch to the positive DC bus and the bottom switch to the negative DC bus, you would get an output voltage of VDC. And if you flip it around and connect the A phase switch to the bottom leg and the B phase switch to the top leg, you'll get minus VDC. So you get bipolar output voltage. And similar to the previous case, by modulating this, you'll be able to get different voltages between plus VDC and minus VDC. And again, the algorithm to do this is shown here. This is pretty easy derivation. It's not even a derivation. It's just obvious. But if you want more details into it, you can look at the material on CUSP website. So the same can be extended to 3-phase sine PWM. You have again the same VDC by 2. In this case, you're looking at it as duty, so it's 0.5. And then you have the control voltage, which is VC into sine of omega t in phase A, and VC into sine of omega t minus 120 degree in phase B and minus 240 degree in phase C. And the duty ratio is just varied sinusoidally, phase shifted by 120 degree to get the output of the 3-phase inverter. Okay, this is the overview of the AC 3-phase inverter and the single-phase inverter that we saw. And this is one of the maybe first topic that's covered in the part 1 of the advanced electric drives course. So we skipped over the electromagnetic, the magnetics concepts. Again, that's also covered in the course. And we looked at the basics of switch mode power electronics. Again, I just glossed over most of the topic. And then we'll now look into the control of electric drives, basically the DC motor drive, in a little bit more detail than we did the power electronics. Okay. So this is the DC motor model. Again, we will not look into the machine design and stuff, which will be covered in the next session by Jim Hendershot in much detail. So the overall concept is just 2 magnets. You have a magnet on the rotor, and you have you have a magnet on the stator, and you have an electromagnet on the rotor. And depending on the position of this magnet, the torque produced is going to change. And in DC motor, it's aligned such that they always are at 90 degree, which is the point of maximum torque production. And by adjusting the applied voltage, you can adjust the magnitude of the flux produced by the electromagnet in the rotor. So by adjusting the voltage, you can adjust the current, which in turn adjusts the flux, which in turn adjusts the magnetic strength of the electromagnet. So it's basically 2 magnets interacting with one another to produce torque. So from equation point of view, the torque of the DC motor is going to be a function of some kT, which is going to be dependent on the strength of your stator magnet times the applied armature current. And this kT is just a function of motor design, and we'll not worry about what the values are. For us, it's just a constant. So your torque is directly proportional to your current, and your applied, your back EMF is going to be proportional to your speed that the motor is rotating at. And again, this is just basic concept of there was Faraday's equation. A rotating conductor and magnetic field produces a back EMF. So, and that's going to be proportional to the speed at which it rotates. So those are the 2 equations. And if you're looking at it in SI units, your KT constant is going to be equal to your KE constant. And your applied voltage equation is going to be equal to your back EMF plus your drop across your resistor plus your drop across your inductor, as shown in the equivalent circuit here. And then the final equation that ties them all together is the relationship between your speed and your torque. So the problem with the DC motor is as you change the load that is applied, the speed of the motor is going to keep dropping. And the reason for that is as I keep increasing the load torque, your current is going to increase as from this equation. And as your current keeps increasing, your voltage your back EMF is going to drop because you have a constant voltage. And then there's going to be more and more drop across the resistor. And that means the back EMF is going to get reduced, which means your speed is going to get drop down. So let us look at this using a simulation and do the same thing in hardware as well to just get an understanding of what happens. And these are all part of experiments that are available on the CUSP website that goes through each and every experiment. So if you go to resources and basic drives, so all of these experiments goes through each and every one of them. So here you have motor control where you estimate. So the previous experiment is characterization of the DC motor where you estimate the KE, KT, and all these parameters that we saw here, the R, LA, J. And once we have these parameters estimated, we can do speed control as we'll see in this experiment. Okay, so let's go ahead and open the first, let's do a simulation of this model that we just saw here. So this is very simple. We have an applied voltage minus the back EMF, and then we divide it by 1 by SL plus R, which is the transfer function, this transfer function, RA and LA. So I'm subtracting the applied voltage minus the back EMF. That should give me the drop across the armature inductance and the resistance. And if I do the 1 by SL plus R, whatever comes as the output is your current, armature current. And if I scale the armature current by torque constant, I get the electromagnetic torque. The electromagnetic torque minus the load torque divided by 1 by Sj plus B, which is this one. So here I'm just showing the equation for inertia. And if I add the frictional component as well, it will become 1 by Sj plus B, this transfer function. So the output of that would be the mechanical speed. And if I scale the mechanical speed by the back EMF constant, Ke, which is equal to Kt in SI units, I will get the back EMF, and I use that to close the loop. So it's just two transfer functions and a bunch of gain block, and I've completed the DC motor model. So let's go ahead and simulate this model. Before I simulate, so what I'm doing is at time 0.1 second, I give a step voltage of 10 volts. And after that, I start increasing the applied load torque at every second by 0.05 Newton meter, or about 50 millinewton meters. This is a really small motor. It's a lab motor. I'll show you the setup in a couple of minutes. So let's go ahead and simulate the system. Okay. So at time 0, you see the speed is some value close to about 93. It's in around 100 radians per second because I'm applying 10 volts and your Ke is 0.1. So 10 by 0.1, that should be about 100. And accounting for like stator drop, it should be a little bit less than 100. And that's what we see here. And at 1 second, I apply 15 millinewton meter and you see the speed drops. And then at second, I apply 100 millinewton meter and the speed drops even further. And it keeps dropping linearly for every step. And that's what we see here as well. As the load torque is increased, the speed of the motor keeps dropping. And this becomes a problem if you have, say, an elevator where you have, if you have one person in the elevator versus 10 person in the elevator. If it goes extremely slow at 10%, and if it goes extremely fast when one person is standing there, that becomes a problem. Or again, in a conveyor belt, or you have a fan, or you have a motor that's mixing some liquid, as the viscosity of the liquid increases, the speed should not change. So if those are the constraints, then this kind of open loop speed, where you just apply some voltage and assume that the speed is going to be constant, that's going to become problematic. So what we want to do, we want to be able to keep the speed constant even though the load keeps changing. So before, let's verify. So this is just simulation. Let's verify if this is what happens in reality as well. So let's go to DC motor real-time speed control. And let me switch over the video. My webcam now shows the hardware setup. So we have a DC motor on the right, and a DC generator on the left, or a DC motor which basically just acts like a load to emulate a load. The first DC motor, again, I'm setting it at 10 volts. I'm going to run it for some time, and then I'm going to start adding load to it, and you'll see the speed drop in real time. Okay, so let's go to real time mode, and let's turn on the power supply. Okay. So the speed is settling at around 90, and it's remaining there. Now let me add a load, and you see the speed just dropped. And let me add one more load step, and the speed drops even further. Let me add 2 more load steps, and you can see the speed drops even further. This is very similar to what we observed in simulation. Okay, and if I reduce the load, it should go back up again. And if I make it all the way 0, it should go back to the original speed. So let's stop this. Okay, so as you can see, the speed keeps changing with the amount of load I applied, and the real-time results is exactly same as what we got in simulation. And again, this is one of the experiments that's part of the advanced the basic electric drives lab. And you can follow along, just go to this link and you should be able to get the manual in the resources section, sorry, basic drives. And you should be able to do all of these experiments and verify the results for yourself as well. And these labs can be done remotely as well. So if anybody is interested in trying out this experiment themselves hands-on, just let me know and I can set up a remote session using TeamViewer and you can try it out as well. Okay. So now, so we verified that both in simulation and real time, the speed keeps dropping as we change. So what we want to do is in the next part, we want to be able to design a control system that can maintain the speed even when the load torque changes. So this is the motor model transfer function that I showed you in Workbench before. So on the left, you have the electrical, on the left, you have the electrical equations, electrical model. And on the right, you have the mechanical model equations. And these needs to be tied together. And that is tied together by the back EMF and the torque equation. So you can think of it in a motor as the rotor element, the mechanical aspect, and the stator element, sorry, in the DC motor, rotor is the where we control the power electronics. So the rotor is the electrical component, and just the you have the rotating component, the mechanical component, and you have those two coupled together by the back EMF and the torque equations. And so the flux, the energy in the air gap is basically what that couples from electrical to the mechanical. So what we want to do is be able to, this is the same model that I just showed you, the back EMF. So this is the electrical model 1 by SL plus R, and this is the 1 by SJ plus B. And then this is the whole electrical and the mechanical model we just simulated right now. And these are all the simulation results. So what we want to be able to do is control the speed of the DC motor even when the load torque changes. So to do that, we'll be using a PA controller. There are different controllers that are available. And the most simplest and the easiest of them is PA controller. Even more simpler would be hysteretic, but that's not used in any practical application because of variable switching frequency, which cause a lot of noise issue and DMI issues. So the very minimal basic that we'll be using is a PA controller. So PA controller, what it does is if there is an error, say I want some particular speed 100 radians per second, and if the measured speed is say 90 radians per second. So it'll take the difference between the two and see that the error is 10 radians per second. So it'll apply some proportional voltage. So it'll apply say 10 volts. And if the error becomes just 5 radians per second, it'll apply 5 volts. And as the error keeps coming, reducing and reducing, the speed, the applied voltage will keep reducing. And if you just had P controller alone without an integral component, when the applied voltage equal to the measured, when the desired speed is equal to the measured speed, the error will become 0. That means the applied voltage will also become 0, which means the speed will start to die down. So we need an integral component which can retain some voltage even when the error goes to 0. So you would need at the minimum a P integral as well as a proportional as well as an integral controller. So that's the overall control system of the PA controller that we'll be using. Okay, so to design this controller, what all we need to do? So we want, we will have to have multiple loops, and so we want to be able to control the inner current and as well as the speed. So if say we want to have the motor run at 100 radians per second, and currently the speed is say 10 radians per second. If your controller did not have an inner current control loop, it will apply a huge amount of voltage at the output, and that can cause huge amount of current to flow into the motor, which might not be ideal, which could burn the motor or the inverter if there is no current control protection. So you would want to have a current control loop as well, which limits the current. So you would have a current controller on the inside, which limits the current, and then cascade it on the outside with the speed controller, which controls the speed. And you should note though that even though you have two loops, it does not mean you can control the current independently. It's just a transient current control of the current and not the steady state control of the current. Steady state is controlled by the outer speed loop. Okay, and if you want to do speed control, you would add one more loop to the speed loop, where the transient speed you can control, but the steady state you can only control the position and not the speed. So here is the overall structure. Again, I won't go into too much detail of it since we are a bit running out of time. So what we have is we have a reference current, and we are measuring the current, and we have a PA controller which controls the applied voltage so that the generated current is equal to the measured current. And this is the overall transfer function of the system, and can be reduced further and further by just moving these blocks around to the simplified form. And this is the overall transfer function of the system that we would like to tune the KPKI values for. So this is a first order system 1 by SL plus R. And this is just a basic first order system. And you have a PA controller, and you can adjust the phase margin and the gain margin of the system to adjust the stability. Usually you would have a phase margin of about 60 degrees. And this is the point where you have just a little bit of underdamped response with a zeta factor around 1 by root 2. And this is very close to the ideal value where you would have minimal error, square error function. So what that basically means is you would use minimum amount of energy required to take it from point A to point B of the desired speed or the desired current. So that's the reason we picked this particular phase margin. It could be other values too. So 60 degrees might not be always applicable. Say in case of a robotic system and assembly plan, you would have a lower phase margin because you want your system to be more overdamped, because you don't want your arm to be swinging around. But say if you're having an elevator system, if a speed swings a little bit here and there, that's a bit fine, a couple of RPMs, as long as it achieves that speed at a desired time, that should be good enough. So depending on the application, the phase margin, gain margin you choose would be different. But 60 degree would get the point where it's very close to the point where you get the minimal energy required to take it from point A to point B. And the frequency of this PA controller, the frequency, open loop frequency that you would choose would be at least 1 by 10th of the switching frequency. So if my inverter is switching at say 10 kilohertz, the loop bandwidth, I would design it to be at about 1 kilohertz. So all of the reasons as to why we choose these kind of values and how to go about designing these are detailed in the course material available on CUSP, as well as on these experiments. There's a theory section where it's given in extreme detail as to the choice and how to go about designing these. Okay. So this is the PA controller design. Again, in the closed loop and open loop PA controller, without the PA controller and with the PA controller in closed loop, you would want to have it similar to a second order system, 40 dB per decade. Okay, so let's go ahead and simulate the system with the PA controller on with the motor model. Okay, DC motor speed control. So here we have the DC motor model. We have a current control, inner current controller, which is just a simple PA controller, and then an outer speed controller. So let's run the simulation. And as you can see in the simulation, at time 0.1 second, I step a reference speed 100 radians per second, and goes to that 100 radians per second as desired. And after that, when I apply a load torque of 0.2 Newton meter at 0.6 seconds, the speed drops a little bit, but the controller kind of recovers and pushes back to the desired speed. So this is the simulation. So this is all achieved by the PA controller. So you have an outer speed loop and an inner current loop. And this inner current loop is just to limit the maximum current. It can only affect the transient response. You cannot control the steady state current in any way because you have only one control variable. Okay, let's do the same thing in real time as well. Okay, so as you can see, this is the same system setup. You have a DC motor, but here instead of just doing open loop, you have a closed loop speed controller here. And then the bottom is the same. I'm going to vary the load, torque, and steps, and see that the speed has remains a constant. Okay, let's go ahead and run it. Oops, sorry, I forgot to turn on the power supply. Okay, it again. Okay, so as you can see, the speed is at 100 radians per second. We'll look at zoom in into transient response once we stop it. So let me apply a load torque of 0.05 Newton meter, and you can see the speed dips a little bit, but it's again still same. Let me apply, like, say, double the load step. You can see again the speed dips a lot, but it recovers pretty fast. And let me apply full load, and you can see, oh, I've reached the overcurrent limit at that value, so the speed is going to go down. But just before the overcurrent limit, if I bring it back up again, you can see the speed remains constant. So irrespective of what step I apply, as long as I don't exceed the current limit, I should be fine. The inverter will be able to generate the desired current. So as you can see, the speed always remains a constant irrespective of the step. So at time 1 second, I apply the step reference, it goes to 100 and settles down at 100 and remains there. And at every other step, as I keep applying load torque, the speed dips a little bit, but it recovers pretty quickly and settles back again. And again, this point and drop is because the inverter reached overcurrent and it went into current limit, but otherwise this wouldn't have happened. Okay, so that is in DC motor speed control. So what we want to achieve in the next, so this is all basically slides for whatever I showed you just now. In the next part of the remaining 20 minutes, what I want to go over is the structure of a AC machine, and why use space vector, why use DQ, and look at induction motor vector control as quickly as possible. Okay, so AC machine and a DC machine, you just have windings that are distributed, a constant set of windings that are distributed across the motor. In an AC machine, you have three set of windings, phase shifted by 120 degree, and their density varies as a sign of the angle. So here I'm just showing the winding density of a phase alone. At angle 90 degree, you have say 10 windings, and at say angle 30 degrees, you would have half of its sine of 30. So you would have 5 windings there, 5 turns at 30 degrees. And at angle of 0, you would have absolutely no windings. So you just, the number of turns that you apply, you just keep reducing the number of turns depending on the angle at which the winding is. Again, the details of it, Jim Hendershot will cover in the next session. I'll skip over it, but all you have to understand is that the windings are sinusoidally distributed, and you have 3 set of windings. So even though you have 3 set of windings, that does not mean you have 3 independent voltages. That is because the neutral point of these 3 windings are tied together. So that means you have only 2 independent variables, because some of these 3 variables, VA, VB, VC, is going to be always equal to 0, because that's equal to the neutral point voltage, and that's going to be floating, and that's going to be 0 as long as these are balanced. And that enables us to transform these from 3 variables to 2 variables. And this can be somewhat intuitive if you look at it in terms of voltage and magnitude. In a DC motor, you could only control the magnitude of the voltage. In an AC motor, you can control the magnitude as well as the frequency. So that gives you 2 control variables. You can't just the phase, because the phase is always going to be 0, minus 120, minus 240. If you had that control variable as well, that would mean you have 3 control variables, 3 independent variables, but we control only voltage and the frequency. That means you have only 2 control variables. So that's how you reduce 3-phase system into an equivalent 2-phase system. And it becomes more obvious when you look at it in terms of space vector. So consider 3 independent variables, VA, VB, VC, or IA, IB, IC. This can occupy the full 3D space. So I've shown here on the right. If you have 3 independent variables, it can occupy the full 3D space. Now say if I limit it by saying it's a balanced system and the sum of the 3 phase quantities are 0, that means if I plot with this constraint, VA plus VB plus VC equal to 0, or IA plus IB plus IC equal to 0, it becomes only 2 independent variables, because the other can be expressed as, say, VA can be expressed as sum of VB and VC, or IA can be expressed as sum of IB and IC. So there are only 2 independent variables. That means if I plot this, all of this occupies just a plane and rather than a 3D space. So this becomes an equation of a plane, the sum of 3 equal to 0. And what space vector does is just does a rotational 3D rotational transformation that converts a 3D system into a 2D system because all of these points lie on a plane. So that's all ABC to DQ, ABC to alpha beta transformation or space vector transformation does. It's converting a 3-phase system into a 3-phase AC system into a 2-phase AC system. And the transformation rotation matrix is given here. So VA space vectors, VA e power j theta, VB e power j2 by v3, and VC e power j2 by 3, 4 pi by 3. And similarly, every other vector can be converted using this. So e power j is just cos of 0, sine of 0, cos of 120, sine of 120, cos of 240, sine of 240. And this is everybody who's familiar with rotational transformation must. Okay. So if we just look at rotational transformation, this is exactly the same. This matrix cos minus sine, sine cos, that's exactly the transformation that you use for space vector, except it's just expressed in e power terms instead of using cos and sines to simplify the expression. So now we have reduced the 3-phase system into 2-phase system. It's still AC though. So we have 3-phase sinusoidal wave voltages. We have converted into 2-phase sinusoidal voltages, which are shifted by 90 degrees. That's all space vector did. It is still AC though. And if we want to do DC motor kind of control, we still need to convert it into DC quantities. But before we do that, we need to understand what these AC quantities are. So let's start with the flux linkage equation. So the flux linkage of the stator phase is equal to the current flowing in the stator phase times the leakage component, plus the flux linkage mutual coupling between the A phase and the B phase, and A phase and the C phase, and similarly each of those. So this is in case the rotor is not present. And similarly, if the rotor is present and the stator is not present, you get the rotor flux linkage equations, which are given here. And if you want the whole flux linkage equation for the stator, when the rotor and the stator are both considered, it becomes the stator flux linkage plus the rotor flux linkage. And similarly, the rotor, if you look at the when the rotor flux linkage is rotating, when the rotor is rotating, you have an e power j theta component as well. That's because when the stator and the rotor are aligned together, this A phase flux linkage couples to A phase at 0 degrees and A couples to B phase at 120. But if this rotor itself starts rotating, the coupling starts changing. So that's what is reflected by this e power j theta term. Again, the details and the theory of it is cannot be fit within this session. You can look at the CUSP website for more detailed slides that professor has online, along with video tutorials. So the problem is, if you want to design DQ control of a PA controller for this, it is still possible. You can design PA controller for AC quantities. All of these quantities are going to be AC. And there's one more quantity which varies with the rotor position. You can still design a PA controller, but it becomes extremely complicated and the decoupling is not nice. So you have components of the fundamental also reflecting your fundamental frequency also coming into your PA controller design. So to eliminate this, it'll be nice if we go to a frame in which our conversion frame itself is rotating. So here, when we went to ABC to DQ, we had a frame which is static, and we are just projecting 3 components to 2 components because it was 2 independent variables and not 3 independent variables. But instead of having a static frame, if our frame of conversion itself is rotating, your AC components will become DC components, and all that we used in DC motor control can be used in AC motor control as well. So that's the reason why we go from ABC to DQ. And to be able to do that, as you can see here, once we go from ABC to DQ, in the flux linkage, we had the theta component. The theta component disappears. It is just products of some constant times ISD, IRD, IRQ, and these are all DC quantities with some transient. So these are all DC quantities, and all of it can be now tuned with a PA controller similar to how we did before. So the transformation matrix to go from ABC to DQ is very, very straightforward. So you have the cos of 0, cos of 2 pi by 3, cos of 4 pi by 3, and sine of 0, sine of 2 pi by 3, sine of 4 pi by 3, similar to ABC to space vector. And then you add it, and you do this transformation in a rotational frame instead of a static frame. So you have the theta component as well here. And that would make all of these AC quantities into DC quantities. So we started with 3-phase AC quantities, and we are ending up with 2-phase DC quantities in our control system. And this is the equation at the end of the day. You have D voltage, which is Rs times Is D plus d lambda by dt. And you have an omega d component because of the rotational component present. This is cross coupling term. And when we design a PA controller, we'll always ignore we will ignore the cross coupling term and then do compensation later. So all we are worried about is the Rs term and the d by dt lambda term. So this is very similar to what we had with the DC motor, where we had V equal to R times Ia plus d by dt of Ia times L. And there we used L instead of lambda because our L was fixed there. And here also L is fixed, so you can just put LLS IS and LMIS as well here. And similarly, you'll have rotary equations as well. Again, those are very similar to the DC motor model that we just saw. And again, I'll skip over all of these. It is just the DC motor model that whatever equations we had before, we are just modeling it using Workbench or again Simulink. All of those examples are available on the CUSP website that you can download and do it yourself. Okay, so let's go to the interesting part where we want to be able to control the induction motor speed control. Let me open the simulation model and explain it from there. So let's go to induction motor simulation. Okay, here we have the induction motor model. All of it is modeled in DQ using the equations that I just showed you. And you have two, so previously we had just one PA controller, one inner current control and one outer speed control for a DC motor. We have the same structure here. In addition, we'll have one more loop which can control the applied flux as well. Because you have two control variables in case of an AC motor, you can control the flux as well as the speed. And in a DC motor, you can't control the flux because that's basically a permanent magnet. Or if you had an auxiliary winding, that would control the flux, and the primary winding can't control the flux in any form. But in an AC motor, you'll be able to control the flux. Even in a PMAC where you have a permanent magnet, you'll still be able to adjust or weaken the flux or add on to the flux by using the additional loop. Okay, so let's go ahead and simulate the system. So as you can see, we have exactly the same response as we would have with a DC motor. At 0.1 second, you apply a step reference speed and the speed goes up. And at 0.6 second, you apply a load torque and the load speed dips a little bit and settles back again. So we have achieved what we set out. Like we wanted the speed response of an induction motor to be exactly same as a DC motor in closed loop control, where if there is a step load change in torque, the speed will still remain a constant. And this is the IDIQ. So the IQ current controls your torque. So let's look at the IQ current. So if you look at the DC motor current that we got, in real time. Okay, so look at the plot on the right. The DC motor current, you have initial step in the current when it's accelerating. Then you have some little bit of current for sourcing the frictional torque. And then when the load torque is applied, the current increases to kind of source the load torque. You see the same in the IQ, the green plot. Initially, there's a huge current for acceleration when the speed goes from 0 to desired speed. And once the speed settles down, the current almost goes to 0, just the frictional component. And then at 0.6 seconds, you see another load component current flowing in. So the IQ current controls same as the DC motor example in an induction motor. And the ID current is always maintained the constant. You can change it, but in this case, we maintain it as a constant at rated flux so that it maintains a rated flux so that the response is very fast. If you had lower than the rated flux, the response is going to be a little bit slower. So that is the simulation. Now let's go ahead and run the same thing in hardware. Induction motor real-time vector control. Okay, let me change over the view to so this is the hardware mode. Let me switch it for an induction motor. So here we have an induction motor setup. And the inverter that I'm showing you is, there was a hardware session, the hardware labs, the demonstration session at 12 o'clock. You can probably check out that again if you haven't seen it to get more detail about the inverter and the motor setup. So we have 3 inverters here. We are using only 2 of those inverters. One is controlling the load torque, and the other is DC motor, and the other is the induction motor, which we are kind of going to be doing vector control right now. And this is the vector control model in real time. So you have an induction motor model. Once I go to real time, this model is going to disappear because you have an actual motor, and you have all the PA controllers and stuff similar to what we saw in simulation. So let's go ahead and run this, and hopefully the speed should go and settle down to the desired value, even when we add a load torque. So this is the result from the actual system running. Oh, let me see here. I connect the USB. So you should be able to see the motor spinning here. I forgot to connect the encoder. I just connected it. You should see the speed now. Got too many motors mixed up the wrong encoder. There we go. So as you can see, at 1 second, I apply a reference speed step. The speed goes to the reference speed, and at 3 seconds, I apply a load torque. And as you can see, the load torque remains, the motor speed remains a constant with respect to the load torque being applied. So again, this is part of the advanced electric drives experiment that is available on this website here. And it's available, the link is provided in the CUSP website as well. And on the advanced electric drives manual, you can do just the simulations alone as well using the Workbench software, which is free to download. Or you can download it from here. Or you can do the remote labs as well, or you can get the lab kit and do it at your home or at your work as well if you need. So that's the experiment on induction motor vector control. We have a couple of more minutes. We can look at we can look at induction PMSM vector control as well, just to complete it. So a PMSM model is very similar to an induction motor model. In an induction motor, you add a rotor winding as well, and in PMSM, there is no rotor winding. It's a fixed magnet. So there is no lambda RD component that needs to be computed. It's just a constant flux, lambda FD, that's the rotor flux. And we align it along the D axis, the rotor. Again, the reason for it is explained in Professor Mohan's course. And you have Q component, which is just function of the applied stator current. So it's just a simpler model of induction motor vector control. So let's switch out to PMSM motor model and run that as well in hardware just for completion. So here is the induction motor PMSM vector PMSM hardware. Again, I have a DC motor coupled to the PMSM to emulate a load, and then I have PMSM here. We couple those 3, and then let me connect the speed encoder. Okay, so let's open up the last part. So the equations are very similar to PMSM induction motor. Let's do the electric drives. Oops. So the rotor position of a PMSM needs to be initialized because I need to know, as I mentioned earlier, D axis is aligned with rotor flux axis. Again, the reason is explained in Professor Mohan's book. So that's an initial step that I need to do before I can run the PMSM in vector control. So once that is done, let me do it once more just to verify it. Yep. Okay. Right, now we should be able to see PMSM speed go to 100, settle down, and the respect of the load torque being applied, it should remain there, hopefully. Okay, there we go. So we applied at 1 second some reference speed, it goes up, settles down, and at 3 seconds I applied a load torque. There's a small dip, but the speed remains a constant. So those are all the experiments that are covered, and there are a bunch of more experiments as well, direct torque control and sensorless experiments, which I didn't go over, but those are available on the website. That is linked online, and as well as I have given a link at the end of this presentation. So that concludes this session on advanced electric drives course. So it's supposed to be a 1-semester course. Originally, it's supposed to be a 3-semester course, which we combined it into a 1-semester course. And here I attempted to combine all of that into a 1-hour session. And hopefully I just was able to transfer some element of information, and more detail, as I mentioned, are available both on the CUSP website as well as the SIAMBL website. And before I conclude this session and transfer the control over to Jim Hendershot, who is going to have a session on motor design, I would like to acknowledge Office of Naval Research, which has enabled us to develop all of these courses as well as the content for the new textbook that's available from Wiley. And all of these labs that are available, all of it was developed using the ONR funding, the previous funding as well as the current funding for future labs as well. And we make these kits available at extremely low cost for everybody, irrespective of commercial use or educational use. The whole purpose is to make it available to as many people as possible at an extremely low cost. And the software, as I mentioned earlier, is absolutely free of cost. With that, I would like to conclude the session. Thanks a lot. And if you have any questions, you can email me or Professor Mohan, and you can visit this website as well. Scheduled to present next in the call. I don't see him. Okay, my bad. So with that, I would like to conclude this session, and let me stop sharing. And here's a brief bio of Jim Hendershot, who's going to be presenting the next session. He has over 40 years of experience in practical hands-on in PM and SR brushless motor design in manufacturing and development. He has been employed at United Technologies, General Motor, Clinton Precision, Burlar, and Pacific Scientific, where he has designed hundreds of brushless motors for computer disk drives, servo systems, high-speed machines, etc. He has also written numerous technical papers, and he has co-authored a textbook, a very well-known textbook with Professor T.J.E. Miller. And if you haven't read it before, if you don't have a copy, I would definitely recommend getting one. It's one of the must-have books on your shelf. He has teaches detailed motor design training courses at various public venues and conferences. Jim Hendershot got his BSc in physics from Baldwin Wallace University, and he also has an additional EE and ME from Cleveland State University, as well as graduate courses from Case Western University. He specializes in design, analysis, sourcing, manufacturing, and teaching of both electromagnetic and permanent magnetic devices. Hendershot has over 40 years of extensive experience designing these motors, and he has enjoyed long and rich association with Professor Miller, and who is the founder of Speed Consortium at the University of Glasgow. Professor Jim Hendershot has developed these dyno kits for us. Those who have used the earlier version of the electric drive slab kit must be very familiar with those dyno kits, and those are still available. He sells both DFIG and induction motor PMSM. The complete kit as well is available on the from Professor Hendershot. Professor Hendershot has created over a series of 37 electric machine designs course that's available on the CUSP website as well. And he'll be giving a brief overview of the course that he has developed. And with that, I would like to conclude and give over the controls to Jim Hendershot. Thank you.
Hey, Jim, we see you, but we can't hear you yet. There we go.
Now,
Yes.
very good. Thank you very much. I'm sequestered in my home here in Louisville, Kentucky, and I thank you, Raja, for your kind remarks and your presentation. That was a very good predecessor to my discussion. The world needs machine designers, electric motor designers. There's a real significant, dire need for electric machine designers. Raja has showed you how to apply them, how to use them, how to best control them. And this is very important, and it's very popular in the university level to learn these things. But when you get out of the university and you need a motor, you can look in catalogs and try to find an appropriate one that will supply your needs. But typically with the new alternative energy initiatives around the world, and with the unbelievable emphasis on electric traction for airplanes, for boats, for submarines, for off-road equipment, for tractor trailers, for much less automobiles, the need for custom designed electric machines that are not available as standard off-the-shelf catalog items from distributors. They must be optimized, and controlling them is super, super important, as Raja has introduced you to. And the university student needs to learn how to apply these and how to perform loop closures that will give you high efficient motor control with, or motor performance, I should say, at the minimum of cost, and number two, at the lowest mass and weight, because mass and weight is super critical. Let me advise everyone listening, and I thank you for all attending. Let me advise you that NASA has over 450 engineers and technicians at two facilities, Ames Lab and Lewis Lab, that are working diligently on the development of transatlantic electric or hybrid electric flight for 90 passenger airplanes with single aisle. So this is going to happen, and it's an amazing amount of effort. We need engineers to design these machines and to concept these machines and advance the various disciplines within the development of the machines and the controllers and the power electronics. So the universities present this gospel to the students, and good university professors will, all of you will try to entice and encourage your students to pursue these endeavors, to pursue electric machine design. We have women around the world now that are looking into the career of being electrical engineers to develop electric machines, their controls, and their power electronics for these exciting new applications. Many universities have electric vehicle programs. The all-electric race, the let's see, I guess it's called the, has something to do with E something or other. I forget what it's called just now, but there are a lot of universities working on those. So what you learn in school at university level is you learn about the exciting, miraculous relationship between the conversion of energy, electrical energy into mechanical energy. And let this left hand represent the OD of a rotor in a motor. Let this right hand represent the idea of the stator. And a tremendous force is created in thin air, in this air gap. The torque, or the force that's produced in that air gap times this radius, gives you the torque applied to the shaft that makes things turn, that makes things go, makes cars go, makes trucks go, make airplanes fly. This is an amazing, miraculous concept. And so these young engineers that are studying this and are interested in developing a motor for an electric vehicle or something like that, they can learn all about the theory. They learn all about the theory from the professors, Maxwell's equations, and all the other concepts that are mathematically proven and shown, and the controls that are tested and documented with differential equations as Raja has shown you. But now when this engineer sits down and starts to design a machine, it's a really challenge for him. Where does he start? So based on my 45 or so years of experience, I've created 36 lectures that are available on the University of Minnesota website. And the purpose of these lectures is to provide some supplemental material that you universities might see fit to use in those instances where you want to teach your students some practical aspects of electric machine design. And so the way I've structured these 36 lectures, the first group of them includes topics that are appropriate for all motor types. Now, I shouldn't say all motor types, because I don't include stepping motors, because they're commodities these days. Very few companies or students or engineers are designing new step motors. It seems like almost all that can be done with the development of step motors already been done. The trick to them is micro-stepping or the controlling of them. So there's not much new things related to the mechanical aspects of designing and building step motors. They're commodities, they're a great bargain, they're very cheap, they're very precise and very accurate. So we don't cover those. Basically, the machine types that are of interest to the world today, and by the way, that might change as some new inventions might come forth, but presently we have the DC motor, which is not used very much anymore because of the reliability problem with the brushes and the commutator. So there's still a lot of them used, but they're not used in new projects, new traction motors for cars, or I think they're still used in golf carts, for example, but not in modern automobiles, trucks, off-road equipment, farm equipment, and marine equipment. The typical machines, or the most favorite machines today, are of course the AC induction motor or the asynchronous motor. And then next is the permanent magnet synchronous motor, which used to be called a brushless DC motor, but since they're controlled just like an asynchronous induction motor is controlled with flux vector as Raja explained how the three current vectors of the three phases are transformed into two vectors. One applies the torque and the other one controls the magnetizing current. And those are done on in the Q axis of the poles of the rotor. So that control technique is used for PM synchronous motors as well. And the third motor type is known as the reluctance motor. The reluctance motor is the oldest motor known. It goes back to the middle 1800s, but it was not a practical motor to manufacture because they didn't have transistors then. They had mechanical switches that they used to switch the phases on and off. And so they weren't very popular until maybe 20 years ago, but they are becoming more and more popular these days. There are two types of reluctance motors. One is known as a switch reluctance motor, which has a rotor that looks much like a gear and a stator that looks much like an ID, an inside gear. And so there's a coil wrapped around each gear tooth in the stator, and those coils are turned off in sets of 2, 4, 6, or 8, depending on how many there are, for each phase, and they're turned on and off like a light bulb is turned on and off. There's no current shaping. It's simply switch the voltage onto the resistance of those coils, however many are either in series or parallel. And the current rises according to the time constant of the machine. And when it's time to turn it off, which is when the next rotor teeth become aligned with the next stator teeth, you turn the previous phase off, turn the next phase off. And that's the oldest machine known. And there's still some of those used for example, the two largest front-end loaders in the world, one is made by John Deere and the other one made by Letourneau in Fort Worth. And both of those motors use switch reluctance traction motors, one in each wheel, made by US Motors, which is owned by Nidec. The other type of reluctance motor is the a version of an induction motor that's got a salient pole, a special rotor in it. And some of those actually have magnets in them, but many of them don't. That's the newest type of reluctance motor. And the reason those are becoming popular is because the stator looks like the induction motor, looks like the stator of an induction motor, and the inverter is almost identical to that of an induction motor. So those are the three motor types, and the lectures 1 through 15 in this series cover some theory, but not a lot of theory, only what's necessary, because your university professors are teaching you the motor theory, and that's not my purpose here. I only present enough that's appropriate and what's needed for you to understand the rest of my discussion. And so the first 15 lectures mainly discuss materials that are used and the losses in the machine, and specifically sizing. How do you size a machine? If your students are going to design a motor for an electric race car or their personal car, where do they begin? How do they know how big to make the motor? What diameter, how long? And so we discuss all those issues in the first 15 lectures, and many more details of that, of how you size a machine, how you pick the number of teeth in the stator, how you pick the number of poles in the rotor. None of the theory teaches you those things. You have to decide those things based on many different reasons and parameters. And we go into that into great detail. Basically, high-speed motors use low number of poles, and low-speed motors use high number of poles. And so we explain all the details of that and show you that. Then lectures 16 and to 22, those discuss the design of polyphase induction motors. And lectures 23, 26 apply to the reluctance type motors, both the reluctance synchronous and the switch reluctance. And lectures 27 through 32 apply to brushless motors or PMAC motors, however you want to define them. And the motors are essentially the same. A brushless motor is essentially the same, can be identical to a PMAC motor, the difference being how it's controlled. And for years, these permanent magnet machines, these permanent magnet synchronous machines were called brushless motors until the control guys decided to control them with D and Q axis current control. And so they changed the name of the motor to PMAC motor, but it's still a brushless type DC motor. And then lectures 33 and 36 offer some supplemental topics relating to the heat sources in electric machines, the thermal diffusion paths. You know, the most significant heat created in a motor is created in the windings, and the windings are in the deepest part of the motor. And so you wind up with the thermal diffusion distance, or the distance within the machine that it takes for the heat to go through all the materials and the air gaps to get to the outside where it can be cooled. We discuss liquid cooling, we discuss air cooling, and last but not least in this last section of supplemental lectures is that I remember in my career that a chief engineer told me one time that the mechanical problems and the design issues in our machines are more significant than the electrical problems. So we have 3 design engineers that are electrical engineers, and we have 1 mechanical engineer, and the mechanical engineer is really swamped trying to keep up with all the mechanical problems. So we discussed the mechanical issues in this last section, as well as some manufacturing methods. And we're going to look at some of these slides now. I assume I can call them up. Did they come up? I hope.
No, we can't see you yet, but
I don't know how to, I brought my slides up, but I don't know how to make them appear on the screen.
in the Zoom window, look for a green button. It says share screen.
Zoom window of God. Share screen. Is that the one?
That is.
Okay, so now I bring this. Now can you see it?
Not yet. Once you click share screen, there'll be another window and you have to select what you want to share. And you'll,
Desktop?
yeah, that should work.
Allow Zoom to share your screen. Share. Does that work?
Not yet.
Whiteboard. Share. Let me hit that again. Sorry about this, people. I've just, this is the first time I've ever used Zoom. A lot of aerospace labs and companies, they won't use Zoom. They use Teams, you see. Let's see, how in the world do I, basic advanced files? Do I hit files? No. Are you there?
Yeah, so it should just be on basic. You should have something highlighted. Maybe it says screen 1 or maybe it says desktop.
It
Should
says
be
desktop.
Okay, so then in the bottom right corner, there should be a blue button that says share.
Okay, I did that.
Okay, now click that.
I did that.
Okay. Do you see anything change? Or do you still see that window?
No, no, I see my, let's see, maybe I have to. No, I keep clicking and nothing happens. Sorry
Well,
about this.
instead of desktop, try selecting one of the other options on the
Let's see.
screen. Maybe your file should appear there that you have open, your PowerPoint.
Hold on.
Or if you like, you could just email me the slides and I'll forward them for you.
Okay, just a second. No,
Sure.
let me do that. How do I gotta forward them to you, right?
Yeah.
Well, they're all on the, on your website. Can you grab them from there or? CUSP?
Yeah, it might take me longer to find them than for you to just email them to me, but.
Okay. Let's see. Copy. Oh, okay, email. Mail, and who do I mail them to? Who do I mail them to? Hello?
Can you hear me?
Yeah.
KELL
KELL
2390
90
at umn.edu.
UMN.org or
.edu.
edu. Yeah, right. I'm sorry.
Yep, no problem.
Okay. Let's see. I guess that'll. This message has no subject. Okay. It went. Okay.
Okay.
There's a lot of files, so it might take a while for them to go.
Yeah.
Sorry about that. Allow Zoom to share your screen. Did it? Do you happen to see these now?
No, not yet.
Well, I don't know why, but they're all on my screen.
Yeah, looks like I just got the email, so.
Okay.
It looks like it's a lot of videos here.
That's what they are.
So
That's
which
what they
one
are.
okay. You want me to show the videos? Or
Yeah, if you can let's see,
Okay.
how about try 5?
5. All right.
Yeah. Let's just, if you're there handy, you can clip through them for me as I.
Okay.
I just wanted to show an example of these. I'm not going to play them. I'm going to, let's see, can I skip through them? Does that work like that? Maybe.
I can give you control. Okay. So if you click yes
Click.
to my request for you to control my screen, did you see a window that said that? Or
No.
I could just try to. All right.
No, I didn't see that. Sorry.
All right. Well, that's all right. I guess I'll play this and then you can tell me when to skip.
I see.
Oh, there you go. Now you can control it.
Well, I can control it now?
Yeah, you're moving the mouse.
Oh, I see. Okay. So also I do it. I see. Anyway, okay, I just wanted to show some examples of, this is the first lecture on machine sizing. And I'm not going to go over every one of them. I want to get it to change here. Okay. So the electric machines are rated mostly on torque and on power, to the extent that you've got to know how you're going to cool this machine. So down through the years, for 100 years, there have been certain parameters that are used as guidelines to size a machine. And one of the originators of this was a professor, M.G. Say, S-A-Y, you can see his reference at the bottom of this slide. He wrote a book called The Performance and Design of AC Machines, London, 1970. But his work goes, that was the last edition, but his work goes way back before 1970. And so he promoted that you design machines based on the air gap stress and the torque per volume of the rotor. And those are, there's a factor that relates those two values. And air gap stress is figured in pounds per square inch. And if you take the swept air gap diameter of any machine, that's the center of the air gap diameter times pi times the length of the rotor, that gives you the swept area. That's the area where the electrical energy is converted to a force. And then if you divide that into the torque divided by the radius, or the diameter divided by 2, that gives you pounds per square inch, or the air gap stress. And then down through the years, motor companies have built machines and tested them and calculated backwards to see what the air gap stress was of a specific machine, for example, that's totally enclosed, a machine that's liquid cooled, a machine that's internally air cooled, or externally air cooled with ventilation holes through it. And Professor Say published a chart way back when on typical values for however your machine structure is going to be configured. You would pick an air gap stress. For example, let me give you an example. The single phase induction motor, not 3-phase, but the single phase induction motor that's used in your in an old washing machine or a refrigerator or a ceiling fan, those typically have an air gap stress of about 1 psi. If you take a servo motor, may use air gap stresses as high as 10 or 15 psi, but they're not continuous duty. They're intermittent duty. They're servos. If you take a power plant generator, that might have an air gap stress as high as 20 psi. Liquid cooled motors that are used in automobiles might have an air gap stress in the range of 10 to 12 psi. So depending on on what your market is and what your design goal is and how you're going to cool it, you pick an air gap stress, and this is only gives you the rotor diameter. Once you have your design pretty well far along, you have to decide what the current density in the winding is going to be, okay? And the phase conductor current density, and this depends on the RMS value of the phase current. And there are numbers for this that are accepted and determined through actual practice down to the last 100 years. For example, if you have an open enclosure motor, and let's start with a closed frame motor with no fan cooling. The maximum current density for reasonably RPM motors, real high-speed motors have a lot of iron losses, so these numbers have to be adjusted. But for a typical grid-powered motor, say a two-pole motor that will have a maximum speed a little under 3,600 RPM, then your maximum current density that you could support with a safe long-term winding would be about 5 amps per square millimeter. If you have a liquid-cooled motor, you could have a current density of 10 amps per square millimeter. In a power plant generator where you have cooling passages through the stator because of the long thermal diffusion distances, the current density can be as high as 20 amps per square millimeter because you've got direct cooling. Some machine tool spindle motors will spray oil, lube oil, onto the end turns of the stator. They're double dip varnish, so they don't short out, but they spray oil on the end turns. Even General Motors, on their original Chevy Bolt motor, they put oil through the center of the shaft that came out around each end of the stator of the rotor by centrifugal force, and sprayed on the inside of the end turns to cool the motor. Besides that, they had a spiral liquid cooling gap around the stator laminations as well. So you can run high current densities, and these are critical ways of cooling a machine if you are going to design a motor for a vehicle that you want high torque and power density. By the way, you can double the power density of a motor by doubling the speed. Interesting. Same torque, double the speed, double the power density. So really you design for torque, not so much for power. You cool for power and you design for torque. So this is the type of lectures they are that, and the other thing that we provide in these, here's a chart of the gap stress. Comes from Say's book, and you can size according to the magnetic loading in the air gap. You can some motors, the rotors go so fast that you have to keep them from flying apart. I've designed and built motors, permanent magnet motors that go 240,000 RPM for the Korean company Hyundai for their electric turbocharger for their diesel engine, 240 RPM. So you have to retain the magnets based on the tip speed. So this is an example of the type of lectures these are that show you how to make the decisions and decide how to go about your design. So let's, if you would, could you change to, let's see. Let's try 7. Would you go to 7, lecture 7?
Yeah. Downloading. All right. Okay.
The
Can you move this still?
can I move?
To move my mouse still. All right, there you go.
Yeah, I think so. Okay. Now, what I want to talk about here is I used to be involved with helping the development of some software simulation tools. The Speed Lab with Professor Tim Miller at the University of Glasgow, with Infolitica in Montreal, and and for many years before we had any of these motor design simulation tools, many years before we had them, machines were designed by analytical methods, you know, equations that were developed from Maxwell's equations that it's kind of hard. I majored in physics in college, and it was difficult for me when I went in industry to remember my studies about the forces on particles that I can't see and try to turn that into the forces in a motor. And so it takes a little adjustment in your thinking to do that. But equations have been developed to analytical methods to design electric machines. And machines were designed that way for a long time before simulation was used. Now, I want to point out one thing about classical analytical methods. When we calculate the flux density in the portions of a magnetic circuit, if you use classical methods, the assumption is, or the result of your calculation is, a uniform flux density across the thickness of the cross section of the teeth and the thickness of the stator yoke and the rotor yoke. But that is not the case. The flux density in those sections is not uniform. It's the flux density is highest at the shortest path and lowest flux density in the longest path. So as machine developments got more serious with respect to controlling them with inverters, you even have sections of machines where the cores are saturated on purpose. For example, that's exactly what is used today for the motors in cars. You actually have to, the back EMF of a PM synchronous motor used in a car is about equal to the DC rail voltage at half full speed. So how do you make it go any faster? Well, you move the current vector in such a way that the flux is moved to saturate part of the rotor teeth. And now when you saturate half of the rotor teeth, the flux that links the stator windings is reduced in about half. So now the quote voltage constant is about half what it was with the current in the D-axis. So now you could go faster. You can go twice the speed. So when you try to design a motor with classical analytical formulas, you can't do it because you cannot predict these kinds of where the flux distribution is in the magnetic circuit. So you have to use a finite element solver. A finite element solver, as most of you know, but I like to think of it this way. If the finite element solver breaks the cross section up into tiny little elements, and the flux density across those elements is still uniform. But since you've broken the circuit up into so many little elements, and you combine them all together to look at the flux distribution, you get a gradient, or you get a very excellent average picture of what the flux distribution looks like. And so the first finite element packages came out, let's see, I believe A.O. Smith had the first one, a motor company, no less. And they were out of Milwaukee, and they sold this in the late 60s and early 70s. And they used Fortran. The user interface was terrible, but that was the first one. And you couldn't use it to design a machine. You have to design the machine first and then analyze it and refine the design after you determine the flux distribution using a finite element solver, which is a set of matrix equations for every one of those little elements. So I wanted to point out the difference between how you calculate things using classical methods and modern methods. And the new modern finite element tools are template based. There's many of them out there now. Some are even free. They're template based, and they have a lot of post processing to calculate the results you need based on analytical methods using the flux distribution from the internal kernel finite element solver. And that's what we talk about in this one. So let's move to let's have a look at slide 20, or at lecture 27, if you would, please.
Yes.
We're going to look at PM machines. By the way, there are very few traction applications in the world that use induction motors. Most of them use permanent magnet synchronous motors, AC motors. The famous electric car company, Tesla, their first motors were induction machines. They were copper rotored. The rotors are made out of copper, not aluminum. And their first 2 or 3 models used induction motors, where everybody else in the world uses PM synchronous motors. And remember, Tesla invented the induction motor, and that car company is named Tesla. So that might have had something to do with why the owner kept the induction motor as his traction motor. The latest Tesla cars, however, have gone to permanent magnet synchronous AC machines, like most everybody else. For a while there, the cost of magnets was quite high, so there was a interest in reluctance machines and even induction machines, and there are some cars now that do use induction machines. I think the latest General Motors electric car uses induction motor in the front and permanent magnet synchronous in the rear, or vice versa. I don't remember. So I've got several lectures here on the PM synchronous machines, which are probably the most common and what most people are going to be involved with, who study these lectures and are destined to become a machine designer. And here's a picture of 2 basic types of PM synchronous machines. The picture on the left is called an SPM, a surface permanent magnet machine, where the magnets are attached to the surface of the rotor. Now, typically, those in small motors, the rotor core, the blue part or the gray part there, is usually solid steel, but more and more these days, those are becoming laminated. The picture on the right is what's known as an IPM, or an internal permanent magnet. And the first commercial introduction in this type of machine in the world was Toyota. The 2003 Toyota had a rotor in the motor and the generator, 2 separate machines that were internal slab magnets like this, and with a stack of laminations that's punched out of the stator. Now that's very important from a manufacturing point of view and how much material you waste. If you build a progressive die to punch the rotor out first and then punch the stator out, you've got the minimum of wasted steel, which you have to pay for anyway, whether you use it or not. Even this requires the use of a square piece of steel to get those round parts out of. So you lose 21% or so of the steel by punching round laminations out of a square piece of steel, even though it's a strip of steel. So in the 2004 Toyota Prius, they discovered that that you could field weaken this machine. They didn't know that in 2003, but in 2004, they discovered you could field weaken this and you could increase the width of the salient pole in between those two magnets, but you didn't want to give up the flux from the magnets by making the magnet shorter. So they put the magnet in two pieces and put it in the shape of a V. And I'm sure you're all familiar with those kind of machines, so that they get lots of flux from the permanent magnet, but they also get a reluctance torque from the salient pole in between them. And this caught on around the world like women's mini skirts, and everybody copied this in various forms and shapes or another. So the only other type of PM machine in a radial gap would be the outside rotor. And those are very popular too. I don't cover those in these slides because they've become so popular. They're called outrunners. And they're used in model airplanes. They're used in these carts that you, let's see, scooters, scooters, bicycles, motor scooters, unmanned vehicles. I can't think of the name. Those little unmanned things that people fly around. They have 4 of these, one at each corner with a propeller on it. So they've become very popular, made in very high volume. And there's a version of those that are made for battery operated power tools. So this particular series of slides here covers PM machines. Now, I don't know if any of you ever thought about it before, but the maximum flux you can create in an air gap is an interesting topic. It's pretty hard to get greater than 1 Tesla in the air gap of any electromagnetic design. But here's a way to do it using Hall-back magnets. And I'm not going to go into detail about what that is, but a Hall-back array of magnets can allow you to get more than 1 Tesla in the air gap. And the other big advantage of this is that you don't need any back iron behind the magnet. So that saves weight and mass, and that's very important in a lot of applications. But the drawback of these motors is they're very expensive because of the manufacturing of all those little slices of magnets. So we go into those things. By the way, in this slide here, here's an example of some of these V-shaped motor designs. The one on the lower left is Ford's 8-pole motor. The one on the right is the original Toyota 2004. Maybe this is the 2010, I'm not sure. The upper left-hand corner is a spoke design. The magnets are internal, but they're arranged as spokes. And each one of those magnets will feed a pole in between them. This is a way to get higher flux density than 1 Tesla as well. Let's see, how are we doing for time? Okay, let's go to reluctance torque, or 23. Let's try 23. Can you please change to lecture number 23?
Yes, 1 second.
Daniel, right?
Yes.
Thank you very much for your help.
No problem.
I'd be lost without it. I remember when I recorded these things, we used a software product that Ned provided me, and I had no clue how to use it. I tried and tried, so I finally hopped on a plane and flew to Minneapolis, and he put somebody with me, and we in a weekend we recorded all these. Remember that, Ned?
Sorry, give me 1 minute here. It's still downloading.
Sure.
Yeah, I remember that. I remember that.
Yeah. I suppose you've noticed already that I've included an awful lot of pictures and color photographs and examples of different kinds of machines. And I think this is very, very important for students that spend all day with theory and mathematics. And this gives them an opportunity to see what real world machines and components and parts in a machine look like. And so I've included a lot of things like that. There's quite a well-known professor in Germany that that has done a lot of lectures on very large machines, power plant generators, and great big, you know, 20, 30, 40, 50 megawatt machines that they only may build 2 or 3 a year. But some of the techniques that are used in those large machines are being used nowadays in motors for traction, for off-road vehicles, and even for cars because of the long diffusion paths, the cooling problems. And so I've included some of his material in some of these slides. I don't remember offhand which one, but you'll find those very useful as well. Okay, are you able to switch that, Dan?
Yeah, sorry, it's I guess I'm having slow internet here. It's should be less than a minute, but
it's not surprising.
Yeah.
Well, anyway, remember the purpose of these slides, which was instructed to me by Ned Mohan, was to offer supplemental practical experience on machine design for professors that might find it useful to add to their teaching. So the students can log on and look at these on their own, or the professor can use some of the material in his presentations, whatever pleases him and is useful for his teaching needs. That's what they're all for. That's all they're intended to be. And this technology in manufacturing moves so fast, it's probably dated in some areas now. Let me give you one example. I didn't show a picture. I have pictures of windings. There's basically 2 types of windings in all these kinds of motors. One are called concentrated windings. The other one are called distributed windings. Concentrated windings wind around a single tooth, and that gives you real short end turns. And that's very important in some applications. And that end turn requirement alone is what make the designer select that type of a winding. The other type of winding is a distributed winding, where each coil spans several teeth. Well, and to do that, you sometimes cannot wind the wire. It's too big. So you have to use multiple strands in parallel per turn. And this is very touchy, and they don't teach you that in school. None of you teach that. And the designer has to learn about that. And so the latest winding technique is known as hairpin windings, where you don't use multiple strands. You use a hairpin winding, or square or rectangular wires formed like a sort of like a trapezoid, I guess, and they're inserted in the slots. And that's the newest thing that's really not covered in any of these lectures, but I encourage you to look into it, because that has caught on like women's mini skirts, and every traction motor company in the world is doing it. General Motors started it. It was first invented by the old Ramey division of General Motors for the Chevy Volt. And then Toyota took a license from General Motors, so theirs is made that way. The BMW i3 is a famous traction motor, high power density motor, high torque density, the highest to date. And they started off with multiple strands per turn with lots of turns, but they've now switched to a hairpin winding. So that's the latest thing. I encourage you to look that up. Okay, this section is on reluctance machines. They're popular, at least the switch reluctance is robust. You could drop it off of a bridge and it'll still run. The reluctant synchronous machines look like this. Well, this up in the upper left-hand corner, invented in 1888, was a switch reluctance machine, where, remember, I told you that the rotor looks like a gear and the stator looks like a gear, but the but it uses special stators and special excitation, like turning on and off light bulbs that have inductance. That's the problem, turning them on and off in sequence. So they came up with, look over here at 1998. This is the reluctant synchronous machine that uses a stator just like an induction motor and uses the inverter out of an induction motor, but you make the rotor like this. This is a picture of one that Tim Miller and I built and tested back in 1989. And these were individually stamped pieces of steel with thick insulation in between them. Then they're all screwed together. So you have flux carriers, that's this part, and flux barriers, that's this part. So this gives this motor saliency, but you can drive it with an induction motor inverter. So it's a synchronous machine, there's no slip. The trick is to maximize the inductance ratio. The inductance in the direct axis versus the quadrature axis. You want to maximize that inductance ratio. Some switch reluctance motors have an inductance ratio as high as 10 or 12 to 1. Difference in inductance between the d-axis and the quadrature axis. But it's very hard to get an inductance ratio in these machines above about 3. So the latest version of these is where this air is in here, you put magnets in there. I say, my opinion is, if you're going to put magnets in there, why bother with it? Why not use a PMAC synchronous machine? But ABB in Europe came out with a whole line of these from 10 horse to 250 horse with the inverters and everything, and they won a Product 100 award in Europe over this with a big splash, a big announcement, but they couldn't sell very many because they weren't very efficient. They weren't very good. They weren't very power dense. So they came out with another line of them by putting magnets in those flux barriers, which really beefed up their performance and made them competitive. I don't think they have all that many applications for them, but there's still a lot of university interest in this world. So anyway, I'm about done. I got 5 minutes. So I'm supposed to allow questions. Was I supposed to allow a half hour for questions? But so I'm going to end this and encourage you to look at these slides. And if you have any questions, ask me or anybody else at the university, and we'll do our best to answer you. And does anybody have any questions today?
Well, Jim, we don't see any questions, but if any questions come through chat box, we'll let you know. Okay.
Sure.
And so, Jim, thank you so much. I mean, I've been saying it all along that one of the strengths of our CUSP courses and curriculum is that we have people like you. You know, this is what we call institutional knowledge. You know, you have more than 50 years of designing machines. And,
You're very kind.
Right? And
You're very kind. You know, I should make a shout out to a famous professor, Tom Lippo, has passed away recently. And that was a great loss. And not long before that, Professor Bob Lorentz passed away. So we've lost some giants in the industry. And both of those professors had extensive industrial experience, Ned.
Yeah.
That's important, as did Tim Miller.
Right.
So at this point, let's encourage as many students and encourage your professors to encourage students to go into machine design as well as controls.
Yeah, no, indeed. I think,
It looks like we do have 4 questions here, if we wanted to get to those.
yeah, go ahead, Dan, if you could read them.
Sure. It looks like from Ted, he says, thanks, Jim. What is the cutting edge of motors today?
Wow. Interesting. Well, it depends how you call cutting edge. I think there's a lot of interest now in axial flux machines. You know, for a long time, it was a dream of many people to put motors in the wheel of a vehicle. But that's been tried in Sweden and Germany. But see, they don't have chuck holes. They have beautiful highways and streets. In the United States, our roads are such terrible shape that the added unsprung weight in the wheels, not sure how that work out, but I know that's a significant interest right now is axial flux machines. I have a shop that builds, we specialize in custom designs, prototype motors, and we have several axial flux projects right now.
All right, thanks. And the next one from David, how common are Litz windings or Robold coils compared to form wound coils these days?
Well, they're becoming more and more common because with heavy conductors and high frequencies, and remember the whole motor is going faster and faster and faster. When you run a motor faster, it gets smaller for the same output power. Okay, and when you go faster, to make it smaller, you increase the number of poles. So permanent magnet machines are increasing the poles. So the Toyota was 8-pole, the General Motors motor was 10-pole, and the BMW is 12-pole. And these speeds are 12 to 15,000 RPM. So the frequency is very high. So at those frequencies, you have things like skin effect and proximity effect, which results in AC losses. The first time I encountered this was for a motor for Ford. It was for a machine tool spindle. It wasn't for a car. And my AC impedance was 105 times the DC resistance. It's the first time I ever ran into it. So that's what Litz wire is used for, is to mitigate the AC losses of skin effect and proximity effect. So they're becoming more and more popular. Now, what you call the other windings, what did you call them? The other robo windings, verbal windings, R-O umlaut. It's a German word. He was a Berlin professor, and he invented that 100 years ago for power plant generators, because in power plant generators, they would use maybe 20, 30 parallel strands of rectangular wire per turn. And they found that due to the proximity effect, all the current would concentrate on those parallel conductors closest to the air gap. And the conductors deep in the air gap had little or no current in them, so they overheated and burned out. So what they did is he invented what's known as the verbal winding, which transposes all of those rectangular strands so that every strand occupies every position in the slot in the length of the stator. Okay, now you can transpose the windings in another way. If you have 4 or 6 coils in series in a phase, you can divide up the length of the slot into 4 or 6 sections and wind part of the conductors 1/4 into position 1 in slot 1, position 2 in slot 2, position 3 in slot 3, position 4 in slot 4, and so on. So you can get the transposition effects by transposing from slot to slot, because you can't make verbal windings for smaller motors. Next question.
Okay, great. Yeah, we have 2 more if we got time. How about optimization of motors? Can you elaborate on an example process?
Oh, we don't have time to do that. The best, well, there are very detailed software programs that allow you to do that with modern high-speed computers. I don't know what they're called. I've never used them because I'm too old-fashioned, but you can put in all the parameters and let it crunch through hundreds of solutions using simulation software and come up with ideal solutions. If you'll email me, I'll look up the names of those softwares and send them to you, but I don't remember them because I've never used them. I haven't had time, basically. I'm too busy. Last question.
And okay, the last one, it says, how can we access these lesson slide packs? They're all on CUSP, did you say earlier?
Yes, they're all on CUSP.
They're all on the CUSP website.
Yep.
And that's all we have.
All right.
Thank you
All right,
very
thank you
much.
so much, Jim. Good to
Thank
see
you,
you.
everybody, for attending.
Yeah.
Thank you. Yeah.
Yes, stay safe. Yeah, thank you.
You too. Be safe, everybody.
Bye-bye. Yeah, thank you.
Bye-bye.
Bye-bye. Bye-bye. So, this is coming to our last speaker, last but not least, Professor Jonathan Bird. Are you there, Jonathan? Yep. Jonathan, oh yeah, there you are. There you are. You should unmute yourself. Okay. So,
Can you hear me?
yeah, we can see you.
Okay, all right, good.
Your
Okay.
smiling face. So let me introduce Professor Jonathan Bird. He received his BS degree in ECE from the University of Auckland in New Zealand in 2000, and the MS and PhD degrees in electrical and computer engineering from UW-Madison, Wisconsin in 2004 and 2006, respectively, my alma mater. So from 2006 to 2008, he was a senior design engineer with General Motors Advanced Technology Center, Torrance, California. From 2009 to 2015, he was an assistant and then an associate professor with the University of North Carolina at Charlotte, North Carolina. He is currently an associate professor with Portland State University, Portland. His research interests include electric machine design, electromagnetics, and controls. Professor Bird's research has been supported primarily by the DOE, NASA, and NSF. So with this brief bio, Jonathan, it's all yours.
Okay, thank you. You can see the screen, okay?
Yeah, we can.
Okay. Okay, so I'm presenting. It's sort of a good follow-on from Dr. Tim Miller. I'm talking about the design of electric machines, electrical apparatus using finite element analysis. I'm based in Portland, Oregon, and we have a power group here that's focused on power electronics, machines, and power systems. And so the course that I'm teaching and is on the CUSP website has three main components. It's got the introduction to the theory behind the finite element analysis technique, and then a second part's on the winding analysis and material modeling, and then the third part is on modeling using commercial finite element software. There is some free software available too, and I'll give an example reference to that too. I'm a little bit old-fashioned, perhaps, in that I like to talk about the finite element analysis mathematical technique as well, not just use the software. So the course, so I'll talk about these three course parts. And so the recommended prerequisites to this course that's on CUSP is the electric machines and drives course, and the electric machine design course by Hendershot, and then the computer programming course is needed. You need to be familiar with some programming, and so there's a number of textbooks on electric machine design. There's not one that I recommend for all the topics. I've just put a few here. There's a design of rotating electric machines is one, and then there's a couple highlighted here that are on finite element analysis. So the first section of the course, I'm just sort of going to go over them briefly, the sections. I'm mainly going to go over the last section on the commercial finite element software and just a few example problems that I discussed in the course. But for the introduction to the theory, you can imagine there's a lot of math involved. So I go over you know, the partial differential equations and the electromagnetic theory and the techniques for that the electromagnetic finite element analysis program uses. So it gives you a knowledge of how the computer programs actually work, and then you can use them from then on in. But I feel it's good to have a understanding of the techniques of the programs so that you can appreciate what's going on and their limits. And so this first part is heavily on a mathematical theory, and then it ends with a project, and that's documented in the CUSP website, where you're given a problem where you have a ferromagnetic region, shown here as omega-1, and an air region, shown as omega-2, and then you model the magnetic field lines going into the ferromagnetic steel, and you do this using triangle elements, because that's how the finite element program works. It breaks down a complex problem into a lot of triangles, and then solves each field value in each one, and then sums up the result. So it's I think it's a good project to work on for, you know, to get a real understanding of how how finite element analysis works, and then in MATLAB it can output plots like this showing the vector potential lines. Okay, so then once I go over some of the theory, and you do a practice problem in MATLAB, the second part of the course is on the winding analysis and material modeling, and so in this section I rely on a number of fillable handouts and written notes. The other part is also written notes. And so I provide these sorts of handouts that they should be on the CUSP website. I'm going to be updating the course next year again. But you can use these. We use these to draw up the windings and analyze operating conditions for the motors. And so, for example, I discussed the star of slots technique. So this is just an example, stator and rotor, and we analyze the winding distribution in this stator. For example, this is just an example, but you know it has 45 slots, 12 poles. How do you distribute the winding over those 45 slots? And we just discuss how to do that using this technique called star of slots. And then through that you can draw up turns function, winding functions. These model the locations of the windings in the particular slots. And then from that, you can actually calculate inductance terms and MMF for the case of being linear. And so with this knowledge of how the windings look in a machine, you can then add up the three phases. For example, this is this example with the 45 slots, 12 poles. In order to do that, a couple of the slots have to have two slots per pole per phase, and then the others have one slot per pole per phase. And so you get this sort of winding function plot, and you can compare that actually with the finite element analysis model. And you know, but this is normalized. So now the finite element model includes the nonlinearities, as I'll briefly talk about. But the winding function analysis allows you to still extract out the harmonics, as you can see on the left and right. I talk about how to understand these. And so you get the 6-pole pairs, which is what we're trying to get, but you also get these other harmonics. So you want to, ideally you want to make a stated design that has minimal other harmonics to reduce losses, but there's trade-offs. So I talk about different windings and how to analyze them. So you can see that to get these types of waveforms, you can analyze them using Fourier analysis. And then I relate these back to more traditional winding factors. So this section covers the turns function, winding function, distributed windings, concentrated windings, fractional slot windings. So we talk about the 3 types of windings, and then I didn't show here, but I go into quite a lot of detail on magnet modeling and graphical approach, and then there's eddy currents and core loss. One very important topic that is not talked about in this is thermal analysis. That's critical for motor design. But a lot of the programs, computer programs, allow you to do the thermal analysis after the finite element analysis, and you can sort of iterate back and forth using the finite element analysis. But I didn't talk about the theory behind the thermal analysis modeling, and in this I don't talk about that in this class. And then the third topic is on modeling using the commercial finite element analysis software. And so on this page, I sort of tried to summarize what most, I'm probably missing some, but the primary the finite element analysis software that is used for electric machines. So, there's others for antenna design and what have you, but these are some of the main ones. JMAG originally comes from Japan. There's Maxwell ANSYS. This is one that Maxwell is a software that ANSYS bought. ANSYS is famous for the mechanical analysis, and then they also have Fluent for fluid dynamics. So you can integrate the 3 softwares together. JMAG also has thermal and mechanical in its package, and you can also export the models to other software as well to do thermal. And then there's also Magnet. That was bought, that used to be Infolitica. That was bought by Mental Graphics, and then soon after that, Siemens bought Mentor Graphics. So this Magnet is it's from Canada, I believe. It's a really good software as well for machine modeling. It's very easy user interface. And then Altair Flux is another one. It used to be called Magsoft. Altair bought Flux, and then they've also got their thermal, the fluid modeling Altair has. So those 2 are coupled quite well with the Altair. And then COMSOL is a more general software. COMSOL motor physics. I wouldn't recommend that for pure motor design, but it does have a motor module, but it allows you to do a lot of other things with the physics modules, and it's relatively cheap actually. If that one, and then for commercial, based on commercial standards. Not university standards, and then there's also one from the UK, integrated engineering software. That's more, it's kind of a general one as well. There is a free software commercially available. It's talked about quite a bit in academia. That's FEM. It's quite well supported by a professor, and there's quite a lot of documentation on that. software. A lot of these commercial softwares can be obtained for free by contacting the representative. If you're interested, you could send me an email. I can get you in touch with them. I actually have all of these softwares except for the integrated engineering one. Most of them are free or just a few $1,000s per year to provide. They usually give the teaching ones for free, and if you want research ones, that's the full version that they sometimes charge you. Depends on how they're feeling, really. Okay. So in this commercial, so in this section, so that the idea here is you go through the modeling, get to know the nuts and bolts of the program. You don't want to do that all the time, so you'd like to use commercial one, but it's good to know the nuts and bolts. And then after knowing the modeling software, try to talk about the theory behind the machine modeling, traditional machine modeling. And then, oh, by the way, in this, there is most of these, JMAG, Maxwell, Flux, I'm not quite sure about Magnet. They all have, most of them have a module in them, especially for motors. So they do a parameter analysis using, if there's traditional motor, there's a parameter analysis that you can use based on lumped parameter, and then you can import that into FEA as well. But if you want to do a more unusual motor, then you need to go straight to FEA. So the third part of the course is sort of is more sort of hands-on or computer on, and I give a number of problems for analyzing magnetic devices using the software that we have in the lab, and so the idea is to apply the modeling theory and the material property understanding to the finite element model, and then I try to get them to compare the accuracy between the theory and the linear lump parameter analytic models, and then you can also verify the accuracy of the numerical models by increasing the number of mesh elements till you don't see a change in the results. That's an important thing for them to notice. And then comparing linear and nonlinear characteristics is another good exercise that students can do using the finite element model. And then, and you can do comparisons with the transformer. I'll just show you one of those. And then you can do comparisons with the harmonic analysis, looking at the fields in the air gap and comparing the harmonics that you see through the FEA and the magnitudes of them relative to the analytic model. So the magnitudes are usually going to be off, but the actual terms should be quite close. The only additional terms should really be from the nonlinearity or based on geometric assumptions that you didn't account for in your model. And so this is sort of a textbook example transformer. The dimensions actually turn out to be a little bit silly, but I should update these. So this is an example of a transformer, but a lot of the things can be seen using this example. And I get the students to model this in finite elements. This is an example of the finite elements, and I believe this was done in JMAG. And then you can see the magnetic flux density. It shows you the values that they're largest in the center because the flux is both concentrated in that center leg. And then you can get the students to look at the field in the air gap, for example, and so you can see that the lump parameter model will assume it's a constant field across the width, but you can see because of the fringing effects, and then you can also see with the saturation comparison too. I didn't show that. you can see a difference. You know, clearly it's not constant near the edges. And then nonlinearity characteristics can be looked at in the class using the finite element program. And so, you know, you enter the BH curve into JMAG or the ANSYS or what have you, the program you have. And then the students can compare the linear and nonlinear models, you know, as a function of current. And this is the air gap flux, magnetic flux density. So you can see the linear model goes up to almost, you know, really high Tesla, which you really couldn't do. And the nonlinear model shows that the saturation kicks in. And so you can really, you know, they can really see, okay, really what happens when you increase the current and how the flux density changes. So you know, it's almost like an experiment, really. It's kind of the best almost you can do during these days. But it gives you a way of visualizing and seeing what the real effects are of the nonlinearity. And then a second example is looking at the magnets. I spend quite a bit of time in the theory section on magnets. And so this is basically, I think, one of the simplest magnetic circuits you could study with a magnet in it. But I think it explains a lot of interesting features because, for example, the winding here allows the flux to flow. And in this example, the relative permeability was made infinite. Doesn't really change the results too much because I get the students to compare with the analytic and the finite element. It just complicates the analytic. So we make the relative permeability really high in the finite element model, and so what you see is the flux is going to flow around, and in this arrangement is going to be going against the magnet, and so you can see that the effect on the magnet operating point, and then you can model it. So you can do the analytic, and then model it in the finite element program. And so in the class, I get the students to compare the size that the magnet would need to be to create a particular flux density in the air gap. If you used ferrite magnets, so ferrite magnets have a relatively low flux density. Oh, sorry, these are both, whoops, no, that's a mistake there. These are both ferrite, oops. I didn't, so that should be ferrite. I'll correct that. The neodymium-ion boron magnet should have a much higher flux density. It should be 1.3, something like that. This example is comparing the two different ferrite magnets and the size they need to be. So that's an error there where it says rare earth. It's ferrite. And so you can see the one on the right, the magnet characteristics are more linear because you know, it's not coming down and cutting out. Whereas the cheaper magnet, and you can see the effects of temperature. Interestingly, the ferrite magnets actually get better with temperature increase. That's the opposite for neodymium magnets. But you can see that the linearity is better. So you want to make sure you never operate the magnet past the knee, because then you demagnetize the magnet. And so we can look at that using the finite element model and comparing with the analytic. So for example, in this case here, we look at different currents applied, and so you move up and down on this operating point, from this operating point. and you can see, you know, we're not near the demagnetization region when we're varying this current around this region. So you need to make sure that your current excitation in the machine doesn't demagnetize the magnets, and so this sort of analysis technique allows you to study those types of things. Okay, and then we also apply the winding theory to the permanent magnet rotary machine. You know, this is just an example motor, and so we this example is for how am I going for time here? This example here is for the 45 slot 12 pole design. And so I get the students for the class to draw up the stair of slots, the winding arrangement, and then you've got the winding configuration, and then you can model it in the finite element mesh, and then you can look at the field. This is with no, in this example, this is with no magnets and only A phase on. And so you can check the field is being created correctly. And then this example is with the 3 phases and the magnets present. So you get these really interesting plots showing the field distribution within the laminations and what have you. And so then, you know, this magnitude is very low because of the current excitation value that was chosen in the example problem. And then from the analysis, you can extract out in JMAG or the finite element program, you select the egg region. And then you can plot the radial flux density, for example, and see it's not all beautifully sinusoidal. In this example, that's because it's a actually in this plot here, it's from the flux focusing design. So you can extract out the radial field. And then look at the harmonics, and so again you can compare the two between the FEA and the analytic, and then of course you can then calculate the torque for the FEA, and this is an example problem where we do lock rotor torque with the 3-phase winding, and this is the output that was obtained in the example problem that's on the CUSP website. So that sort of summarizes the course that's talked about in CUSP. I actually like to write a lot on the notes, and so I give out handouts, and then I write the notes out, and then show examples with the computer. But I like to write out notes, not just rely on PowerPoint as I'm doing now. So it's definitely a graduate level focus, and the course assessment is primarily homework and project based, and then I use a commercial and free, and there's free software also. I've not actually used the free software because I've got the commercial software for free, like I said, but relying on one of those, I think really the students really enjoy that, and it's like looking at it's like using a microscope to look inside of a motor. Really, you can really see what's going on and where the flux is saturating, the field is saturating the material. So this is sort of a course breakdown with the lecture description as it stands at the moment. So there's quite a lot of mathematical theory. I actually put the theory at the end and done it opposite now. So I kind of start with lecture 8 and then I go back to the mathematical theory at the end of the class. That's how I'm structuring it now. So you go straight in, you go more into the theory, and then of winding analysis and machine design, and then you go back and look at the mathematical modeling. I'm going to teach this class again in spring 2021. I'm hoping I can update the CUSP website with those lectures at that time. And then I wanted to finish with there's lots of machine designers. Machines have been around a long time, but in my opinion, there's a lot of really exciting topics currently, and looking into the future. And that's there's a lot of interest just at the moment on electric planes. How are we going to make an electric plane go across the country? They're talking about that with the ARPA-E and NASA. Got funding solicitations out on that. That's a really difficult problem, and electric machines are part of the solution. Drones, electric cars, of course, and then wind turbines, ocean generators, maglev. There's a lot of electric machine related interesting topics to get students interested in machines. It's not just a static. It's not just static in research. I think there's a lot of exciting research being done at the moment in electric machines, and so some of the topics that I'm working on are magnetic gears, magnetic springs. So there's a bunch of different interesting topics that there's still new things to discover, and I think I try to also try to use examples on those. When you talk about electric cars, for example, that sort of gets students more interested in these topics. Okay, that's I think that's all I have. I think I might have finished a little bit early. Is there any questions? Do we have time for questions?
Yeah. Dan, there are some questions, right?
Yes, it looks like we have one. Okay, no, we have two. Are these codes made available in the course content? I'm not sure what that was referring to.
Well, the code, this so this software is these are from the vendors. So I've provided the websites, and actually I have contacts with most of these companies. JMAG and ANSYS. I mean, I don't want to speak. They're all, in my opinion, they're all pretty similar. They of course would not say that, but they all sort of do the same sort of modeling. They're just different ways of doing it. There are some, improvements here and there, but these are. Then there's the free software. FEM is a free one. The MATLAB code that actually I get the students have to actually make it themselves to pass the class really. So that they have to make. So I try not to make the MATLAB code available because you have to write it. MATLAB does actually have a finite element, basic finite element solver in it as well. But if you really want to get into machines, one of these softwares would be the way to go. JMAG has been giving me their software for free. ANSYS charges a little bit, and then if you're a Mentor Graphics affiliated university, you can get Magnet for free, and Flux Altair is usually for free. ComSol charges a little bit. Yeah, that's all I have on that.
Okay, it looks like we have one more question. What method would you suggest to analytically solve a PM motor problem in 3D?
In 3D? Well, it depends on the motor topology. So if you can start with 2D, then you know, you can model the machine in 2D first, and then you could do that analytically. But really, the finite element programs are going to be needed if you want to model most machines in 3D. Like for an axial flux machine, the flux is 3D inherently, and so you know, you really need to solve it using the finite element modeling. I mean, the analytic models are going to give you a linear result, right? So you're not going to get you're going to get a model, and then you're going to have to iterate on that model using the finite element analysis if you rely on analytic to start with. But I would recommend you find another person that's done a similar machine, and then try modeling that in finite element analysis first, and then that could give you a starting point. But I'd have to know what sort of machine it is, really.
Okay, Jonathan, thank you very much for an excellent presentation. So this is one of the courses that has disappeared, as far as I understand, from most universities. At our university, I had a mentor, Professor Mahmoud Riaz. I used to teach that course, and last time he taught was 35 years ago. But we still need this knowledge. So, you know, I say that this is the strength of this CUSP curriculum, that we have courses that are not easily accessible. And we have experts like you who have put this material on this course website. And someday, you know, you may, you know, if Dr. Gieselman gets going, you may be willing to teach these courses online to graduate students and professional practicing engineers. So thank you again, Jonathan. You know, excellent presentation, and we hope to see you in person one of these days, right? So,
yeah, thank you very much too. It's I mean, doing this online is I mean, that's what we have to do at the moment, isn't it?
yeah, yeah. And you're in Portland, so stay safe.
Yes.
Downtown.
Yeah.
Okay, don't go
Thank
downtown.
you too. Yes. Yeah, I'm not going downtown.
Okay, good, good. All right, all right.
Take care.
Bye-bye. So we have an open discussion starting at 5. I don't know how people are doing other tracks. So we were in electric machines and drives track, but we have power systems and power electronics track, and we have open discussion at 5. So Jonathan, if you're around, if you want to log in at 5, that's okay. If you don't, that's okay. And so Dan, do you have any idea what's going on in other tracks?
Yeah, it looks like Pratap's just finishing up. They're just answering questions at the moment.
How about power electronics?
I hopped out of that one. Give me one. Looks like they're just finishing up as well.
Okay, okay. So let's, you know, there's no reason to wait till 5. Once they're all done, we could start. So Dan, I have a question for you.
Yes.
For this open discussion, Can people raise their hands and speak, or what can we do?
So they can raise their hands or type in the chat box.
Okay.
If they raise their hands, I can allow them to ask their questions audibly, and we can have some discussion that way if we would like, or we
Yeah,
can just
yeah.
type in the chat
Yeah,
box.
if we can let them speak.
Yeah.
They can of course send it through chat box, but if they can speak, that would be tremendous. So we should tell Bruce and Bill that as soon as they're finished, they should let us know and we can start the general discussion.
Okay, I will.
Okay. Okay, Dan,
Yes.
I think we should also tell them to direct their participants to this General Fashion electric drive track. You know?
Yes. I've done that in both the links. Professor Robbins' session is done, and they had the link, and I'm waiting for them to finish questions in Pratap's, and I'll provide them the link there too.
Okay, good. So basically, we'll keep quiet and listen, you know, what suggestions they may have for us to move forward. Okay, Bill, we can see you. Yeah, we can see, hear you, Bill,
Okay.
but maybe turn on your video. Yep, we can see you as well.
Okay.
Mount Rainier. Is that Mount Rainier?
That's right.
Yeah.
I'm surprised no one asked in my session what that mountain was.
Yeah, that's disappointing. maybe they knew. Maybe they're
Could
too.
be.
Yeah. Can you see that from Seattle?
Well, not that particular view, but you can see Mount Rainier from Seattle.
I've seen. What do you see from Portland?
Portland, you don't really see Mount Rainier unless you're in a pretty high hill. What you see there is Mount Hood.
Mount Hood, yeah, Mount Hood. Yeah.
It's about 11,000 feet. Mount Rainier is about 14,000, a little over 14,000.
Mm-hmm. Yeah. Let's see, chat box. Okay. All right, Richard. Yeah, please. He says, Richard from Alaska. St. Helens from Portland. Who says Jonathan Bird? Yes, please.
Yeah, that's true. You can't see Mount St. Helens, so not as well as you used to. Before 1980, it was more visible.
Mm-hmm. Really?
The power systems track just finished, and they should be coming over shortly.
Okay. Mount St. Helens. That's what Jonathan Bird is saying.
Yeah.
So see Mount St. Helens from Portland.
And probably Mount Adams, too.
All right. Okay.
Which is about 12,000 feet.
Yeah. Sure. Power systems track has a lagging power factor. I agree. Oh, there's Bruce.
So we just ended our meeting. We had a wonderful discussion with the attendees. We had about 25 at peak.
Oh, wow.
And we ended by giving them this link and told them to come on back, and we're going to have our final wrap up here. So we'll see how many get back in. I see one. There's one on chat here. Rich.
Yeah,
Conductor.
Well, you have to, there are several messages on chat before that one.
Yeah, all right.
You got to read them all before you understand it.
Okay. So, 34. We have 34 attendees still out there.
Yeah. So
one of them was from Columbia. Talked to me.
okay. Very nice.
And I told her she can see all the web, but the CUSP things, but she can't get the homework problems.
Yeah.
Is that still the case?
I don't know. I have to check. I'll have to check. But certainly not the solutions.
That's what I said, not the solutions.
Yeah. No, I can check. So I think, Bruce, we should start. And like I mentioned before, if you think that's a good format, is that we need to just keep quiet and let the participants tell us what we have done, what they think of it. But primarily, where do we go next from here? You know, would they really would like to see some kind of courses being offered, and would they have students who may be interested, or themselves they may be interested to brush up on certain things? Like, let's say you want to teach a course in finite element analysis. Well, you can look at the material that Professor Bird has put together, but it's not the same as actually taking a course, right? So if what Michael Gieselman is dreaming of, these courses could be offered, then faculty could take those courses too, not just students, if they are thinking about teaching that course, right? It's just my 2 cents. So if anybody has any suggestions, please raise your hand. And Dan Kelly say that he will allow audio for you. So, anybody? So I think it's like in our classes, Bruce, nobody asks any questions. Yeah.
Get all done and you say, are there any questions? Silence. You know, it sometimes it occurs to me that if the class is quite noisy, you ought to stand up and say, are there any questions? And they'd all quiet down, right?
They're tired, going since 6 a.m. Well, that's for Richard in Alaska, right? And tired. So Jonathan raised his hand. So Dan, can you unmute Jonathan?
Hi, can you hear me?
Yep.
Yeah, I'm just curious what you think, because there's quite a discussion amongst the faculty in our department about online classes versus in-class. With these specialty classes that are not taught by many faculty in different universities, I see a good niche. But if all classes are taught online, we could end up with just 20 universities, and then everyone else. But I think based on our discussions, students, there's a mix of students' preferences, but there's a significant percentage of students that like being in class, I think. So I think my conclusion is we're going to be safe. But I was curious what the thoughts are on that. You know, you could have just 20 universities that teaches everything, or will it continue to be distributed?
Yeah, no, I think it's a tough question. I don't know what other people think, but given the cost of education today, I read an article that good 500 to 1,000 colleges and universities may close, may shutter, because they may not get, and this is, these trends were there, Jonathan, even before COVID-19. They have been just accelerated by this pandemic. So,
but the cost of college when you were young, and you know in the 80s and 70s was a lot lower. It was a lot more affordable. It doesn't seem, the current trajectory doesn't seem sustainable. So I don't think that's necessarily just online. It's there's a lot of dynamics there. But something is going to have to change, because if the cost is, can't keep going up 8% every year.
Yeah. No, I agree. So,
let me comment on that. We've talked about this when I was back teaching, and we used to say that the online courses, for example, are ideal for an engineering master's program where you don't have a lot of lab work. Obviously, if you and where that's very, very important is where you have a person working in some city, and it's a couple hundred miles to the closest university that might have labs that they could use. Well, how can they get a master's degree? They can do it online, and I think that's quite popular. But I don't know about costs. That's another thing, and I think that the online courses. Well, let's face it. I have a granddaughter that's just starting at the University of Minnesota nursing, and she's a little upset that all but a couple of the courses are going to be online. She doesn't want them. She wants live classes. And but of course, for nursing, there's a lot of, I hate to use the term hands-on, because they do go into hospitals and work with the staff and things like that. They have to still do that to be able to practice. So that there's a lot of fields where lab work and where, you know, that kind of actual practice with other faculty and staff has to take place. And so those, but boy, for class, just classroom. And you know, when you think about it, large lecture halls, these horrible pictures of lecture halls with 500 students sitting around, and one lecturer down there. I say horrible because the student doesn't get any individual contact with that professor unless they make a big effort, and they probably would have to stand in line after class with a bunch of others. Those kind of things are a candidate for more online, especially if it drops the cost, especially if online courses can drop the cost. But I do agree that the promulgation of online courses may see the shrinkage of a lot of university positions and so forth in the future.
I think you'll recall that there's two examples of universities that have large online course enrollments. Georgia Tech for their master's program, and I think it's the University of Arizona or Arizona State, I forget which one, has a very large online program. And what they have found is the online courses appeal to a different segment of the population compared to the in-person. the online courses appeal more to the older student who's working either full or part-time. And and that has not, they haven't seen much of a shift in their enrollment of the typical undergraduate in the 18 to 22 or 23-year-olds. And so I think, and this was well before COVID came along. And so I think that there's going to be a place for both, because a lot of students, particularly undergraduates, prefer to interact with their peers, whereas older students who are more mature in some respects are much more focused on just getting the information and getting on with finishing the degree as quickly as possible. Now, there is cost differentials in some of these programs and others there's not, and I can't speak to that. But a real bottleneck is a certain amount of lab work is essential in engineering fields, and it's difficult to give them the full spectrum of the lab experience online. You can do a few things and some work reasonably well. For example, if you're in an electronics course and you can't give the students access to any hardware, well, simulation with PSpice or something like that, it's probably an alternative. Now, in some cases, there is hardware available like the Analog Discovery 2, which is basically a full electronics package, admittedly low voltage, but in some of our beginning electronics courses, that's all we work with anyway. And that can be off, sort of online, or because the student can buy that, or they can rent it. But the problem right now is you can't order Analog Discovery 2 until the beginning of next year, the earliest, according to the manufacturer's website. So there's all kinds of problems with trying to give the full lab experience. And part of the lab experience is not just verifying or seeing the theoretical topics elucidated experimentally. It's also getting the practical experience of how to wire a circuit, how to use the instruments, and so on.
The same
Bill,
would go for physics and chemistry labs and things like that, all the way up through.
So Bill, what do you think of making labs online?
Well, that's what I was trying to speak to. To some degree, labs can be online, but not completely. I've had a couple of experiences because of COVID with labs online, and I was running our junior electronics lab, which is a separate lab course, and halfway through the semester we had to go online, and for the moment the only way I could think of doing it was I did the experiment and recorded it as a video, and then the students had to look at that and look at the experimental data, put it in their lab notebooks, and they were graded mainly on their quality of the lab notebooks. This summer we ran a full beginning circuits course that has a built-in lab, and the lab was done online, and the way it worked was the TA in the lab hooked up a couple of the circuits to the instrumentation. The main piece of instrumentation was an oscilloscope, which could be accessed remotely. And the students, it had a built-in web page, which gave them what was called a remote front panel. And they could control all of the controls remotely. And most of that worked out pretty well, except for a couple of major things. And that was, if you wanted to change the frequency of the function generator from 10 kilohertz to 50 kilohertz, you did it by pressing your mouse button hundreds of times, because the increment in frequency was about 1/10 of a kilohertz. But fortunately, it was possible to program the oscilloscope using LabVIEW. I mean, not LabVIEW, but MATLAB. And so we used the MATLAB program to do that. I wasn't running the course. It was run by someone else, but Professor Abini in our department was the one who developed those labs. So that can be done in some circumstances. And if you're in a microprocessor course where everything is probably already computerized, you can probably do that more effectively than you can an analog circuits course. So there's all kinds of permutations that one can get into, but I would argue that it's still somewhat inferior to the full in-person lab experience. But certainly, given the circumstances we face right now, we're going to have to do some of our labs online.
What I would say that at master's level, most courses do not have hardware labs. Very few that do. So if you look at power curriculum views, until we introduced this electric drives lab, at the graduate level, we really didn't have any graduate level labs. Most courses, if they had some laboratory component that was more computer based, right? Which does not require them to come physically to the university to do any hardware experiment or any experiment whatsoever. So I think if these courses are to take off online, probably they should be at the master's level before they permeate the undergraduate level, where still camaraderie and socializing and other things are very important. So that's my take.
Well, we probably ought to ask, are there other questions, not just on this topic, but what we covered in the webinar?
Mm-hmm. Yeah. Anyone? 28 participants, so.
Of course, I haven't even figured out how to raise my hand.
So, but they certainly can write to the chat box, right? And but I don't see any raised hands or anybody writing anything to the chat box. So I think
there's one then.
Oh yeah, there is one here. Are any plans to developing professional courses such as industrial substation design? So I would say, we haven't really thought about that, but that could be a very good topic, right? This Sobelman at, what's his name? There was a guy at Excel, Bruce, who used to teach.
Yeah, Sheldon Silberman.
Silverman.
Yes,
right.
Sheldon Silberman.
Yeah, he used to teach substation design as part of UW Wisconsin, extension courses. So thank you so much for that suggestion. We have to look for it. Yeah. And full course on distribution system. We really don't have one, except this Michael Rapp had given an UMC presentation. We have that recorded, but using Professor Kirsten's book, isn't there one book from Professor Kirsten on distribution systems from University of New Mexico, Bruce?
Yeah, Bill, oh boy.
Kirsten or something? And,
yeah, but I'm trying to think of his name, but I first name was William, but I'll think of it tonight in the middle of the night, so I can't think of it now. There aren't that many books on distribution. There's a couple that were published in the 90s, 80s.
Yeah.
This is a good question from Luke Weber. Ned, do you want to take that? That's a good question.
Well, Luke, we, I don't know how to answer this, but we have been careful as to what to include as full courses into CUSP. But what we could do going forward is give a link to what you have developed. How would that be, Bruce and Bill? That, but I think, IEEE PES, for example, I just got an email from Christina Chen from University of British Columbia that IEEE PES is soliciting courses that people have developed, and they are putting together a repository of such courses. So I sent her the link for CUSP.
I would, to start with, the people that developed the courses for CUSP, when you started it, you looked towards people who were known experts, to just put it for common language there. In other words, you looked for people who had written many good papers, who had a lot of experience, and so on and so forth. Now, Luke, I don't know if Luke is if he is looking to have a course put on there, but I don't know him, and we'd have to evaluate it. But that's the way you started it out, by just talking to various people that you knew who were the top people, or well enough known. I don't know, have we ever had anybody solicit from the outside? We've never had to do that, have we? We've never had anybody say, I'd like to have my course.
No, we have had such requests. We have.
Yeah.
And so I just told them that, we have been careful in terms of, see, have you seen this confusion chart where there's not enough information, lots of confusion, and there's too much information, a lot of confusion. So there is something in the middle, which is the best, right? So, we have been somewhat careful in terms of who we have asked and whose courses we have put on our CUSP website. But certainly what we could do is have a section where if you have developed a course, you can keep it on your website, and we can provide a link to it, And and that's what exactly what IEEE, Power and Energy Society's this education committee is doing. And that could have a much bigger reach than CUSP, because we are not well known as well anyway as compared to IEEE PES.
Luke makes the comment here. He says it's okay to say by invitation only, but I think, Ned, that it might be good to have a place on the web page that simply requests people, if you have a course, tell us about it, show us some of the materials, and we'll have it gone over. I think that's there might be some people out there that have developed special courses and would like to put it there.
Yeah.
Just say, and then it would just be evaluated, because you want to make sure that it has all the right material and things.
Well, at least we can put a link to it, right?
Yeah.
Just like IEEE PES is doing.
Okay, Ned, I'm going to have to sign off. I have to go pick up dinner at Chianti Grill.
Okay.
Oh.
All right. So I think, so thank you so much, all the good comments. And somebody says, so long, Bill. Luke Weber is saying that. And somebody is saying, C. Cola, thank you for organizing this very informative workshop. Okay. And it's okay to say by invitation only. Yeah. And so, okay, thank you so much. I think we have run out of steam, so to speak. We are no longer in steam locomotive business, but we have run out of steam. But it was, by all counts, it was a very successful workshop. And I would like to, first off, thank all the panelists, all the presenters who, all were excellent. You folks did all wonderful job. And also to all the attendees that you made this workshop possible. So, to finish off, everything that transpired in this workshop is being recorded. And as soon as these recordings become available, we'll send you the links for it. Okay. So if you have any questions, any comments, please feel free to reach out to any of us, and we try to get you the answers if we can. I don't know if you have the answers, but we can try. So thank you all very much, and have a good evening, and hope to see you in person someday when this COVID-19 is over. Okay, and maybe next year we'll have an in-person workshop, and let's dream big. Let's say we'll have it in Hawaii. How's that? Okay, all right. So good night, everybody, and see you. Bye-bye.